This is a beginner-friendly introduction to common data structures and algorithms in Python. This course is taught by Akash Ines, the co-founder and CEO of Jovian.
Data structures and algorithms in Python is a practical, beginner-friendly, and coding-focused online course that will help you improve your programming skills, solve coding challenges, and ace technical interviews. You can also earn a verified certificate of accomplishment by completing this course. Learn more and register at pythondsa.com. This course runs over 6 weeks with 2-hour video lectures every week with live interactive coding using the Python programming language. You will get a chance to practice and improve your coding skills with weekly programming assignments consisting of real interview questions, and you will also build a course project that you can showcase on your resume or LinkedIn profile. This is a beginner-friendly course, and some basic programming knowledge will help you follow along with the course. Don't worry if you're new to programming, you can learn it as you work on this course with a little extra effort. You will also get to access the course community forum where you can ask questions, participate in discussions, and share what you're working on during the course. This course is created by Jovian, a platform for learning data science and machine learning, with a global community of tens of thousands of learners from over 150 countries. I'm your instructor Akash, co-founder and CEO of Jovian, and I'm really excited to kick off this course with you. Register now and invite your friends to join the course at pythondsa.com. Hello and welcome to Data Structures and Algorithms in Python. This is an online certification course brought to you by Jovian. And today we are at lesson 1, binary search, linked lists, and complexity analysis. My name is Akash. I am the CEO and co-founder of Jovian, and I will be your instructor. You can find me on Twitter at @AkashNS. This course runs over 6 weeks, and over the 6 weeks, if you enroll for the course, work on 4 programming assignments, and build a course project, you can earn a certificate of accomplishment. Along the process, you will also learn about common data structures and algorithms in Python, and how to use these skills to ace coding interviews and technical assessments. So let's get started then. To begin, we need to go to the course website, pythondsa.com. So if you open up pythondsa.com in your browser, that will bring you to this page. This is the course page, and you can watch an introductory video about the course here. You can enroll for the course for free. You will need to sign in into Jovian. You can use your Google GitHub or email to sign in into Jovian. And once you're enrolled into the course, you can also invite your friends to join the course. The course is still open for enrollments. So please invite your friends and colleagues. This course is a beginner-friendly introduction to common data structures and algorithms in Python. And this course will help you prepare for coding interviews. We have coding-focused hands-on video tutorials every week. So you can either follow along with this video, you can pause and run the code as we speak, and you can practice coding on the cloud, or you can watch the video right now and you can practice later. In this course, we will solve questions from real programming interviews, and you can earn a verified certificate of accomplishment. So let's go to lesson 1, binary search, linked lists, and complexity. On the lesson 1 page, you can see a recording of the lesson once it is completed. And you will also be able to see a Hindi version here. And all the code used in this lesson is linked below. So the first set of code that we will look at today is called linear and binary search. So let's open it up. So this is the first tutorial that we will work through in this lesson, and you will be able to work through it as well. And this is part 1. And there are a total of 12 notebooks or 12 tutorials we will go through. Now this course assumes very little background in programming and mathematics, but you still do need to know a little bit. For instance, you do need to know basic programming with Python, things like variables, data types, loops, and functions. And don't worry if you don't know them already, you can click through and follow these links. Each of these is a separate tutorial. The tutorial will take you about half an hour or so, each of these, and you can learn the basic programming with Python in just a couple of hours. You will also need to know some high school mathematics And if you want to brush up things like polynomials, vectors, matrices, and probabilities, you can click through and read these. But no prior knowledge of data structures or algorithms is required. You do not need to have an extensive coding background. And we'll cover any additional mathematical and theoretical concepts as we need as we go along. So how to run the code? What you will see here is some explanations, and then you will also see some code. So you can see here that there is some code written here, and there is some so the library is imported and a function from the library is used here. Now to run this code, you have two options. You can either run this code using free online resources, which is what we recommend, or you can run it on your computer locally, and you can read these instructions. I'm going to use free online resources provided by Jovian. So we just scroll up here at the top of this page and click run, and then click run on Binder. So this will take a second or two. And what we're doing here essentially is setting up a machine for you on the cloud using a software called Binder. It's an open source software. And now what you were looking at here, this was actually not a blog post. This is actually something called a Jupyter notebook. A Jupyter notebook is something that can not only contain explanations, but can also contain code, and you can look at the code and its outputs right here in an interactive fashion. So if I scroll down here, you can see that we have all the same content that we were looking at, except this time we can actually run this code. So we can click the run button here, and the run button will run the code. And here we click the second run button, and that is going to run the second line of code. Now we will be using Jupyter notebooks extensively throughout this course, because Jupyter notebooks are a great way to do interactive programming. You can change the code. For example, instead of the mat.square root, you can use mat.ceil, and you can change the value here. So Jupyter notebooks are great for experimenting with code. Now, just a couple of tips that you want to do as soon as you run a Jupyter notebook. You can click on kernel and click restart and clear output. What this will do is this will remove all the pre-executed outputs from your code. So you can now see that the output of the function is gone, and you can see that the numbers here go away. So now you can execute the code line by line yourself and see the output, discover the output. And then one other thing you can do if you want to hide the UI a little bit is to toggle the header and also toggle the toolbar. Now you might need the toolbar for the run button, but there's a tip here. Instead of pressing the run button, you can use Shift plus Enter. So if you press Shift plus Enter, that will execute a cell, and that's a pretty handy shortcut. So once again, you go on the lesson page. On the lesson page, you will find a link to the notebook called Linear and Binary Search. On the linear and binary search, you can read the explanations, but you can't run them. To run the code, you need to click run and then select run on Binder. And clicking run on Binder will set up a cloud machine for you. And all the code that you see here will get executed on the cloud. So you do not need to set up anything on your computer. You do not need to download anything. We've done all that for you. So let's get started then. So this course takes a coding focused approach towards learning, and in each notebook or each tutorial, we will focus on solving one problem and then learn the techniques, algorithms, and data structures to devise an efficient solution for that specific problem. We will then generalize the technique and apply it to other problems. So in this specific tutorial, we will focus on solving this problem. And here's the problem we're solving. And this is a typical problem that you will come across in a coding challenge or a coding interview. So here's how the problem goes. Alice has some cards with numbers written on them, and then she arranges the cards in decreasing order and lays them out face down in a sequence on a table. So this is what it looks like. These are cards. Each of these cards has a number below it, and the numbers are in decreasing order. She challenges Bob to pick out the card containing a given number. For example, she could say, Bob, I want you to pick out the number 7 by turning over as few cards as possible. So this is a puzzle that's given to us, and we're not told how many cards Alice has. So you need to write a function to help Bob locate the card. So Alice can put down any number of cards, and the target number that Bob has to pick out could be anything. So we have to tell Bob not not the solution for a specific problem, but a general strategy that he can use to turn over as few cards as possible. So for instance, look at these 7 cards and maybe put some imaginary numbers below them, and try to figure out a strategy. Try to start thinking about the problem. And this may seem like a simple problem, especially if you're familiar with the concept of binary search, but the strategy and technique that we're learning here will be widely applicable, and we will soon use it to solve harder problems. Now, while you think about the problem and before we start solving it, I just want to talk about why you should learn data structures and algorithms. And whether you're pursuing a career in software development or data science, it's almost certain that you will be asked programming problems like reversing a linked list or balancing a binary tree in a technical interview or coding assessment. Now, it's well known that you never face these problems in your job as a software developer. So it's okay to wonder why such problems are asked in interviews. And they're asked because they demonstrate the following traits. And these are very important traits for a programmer. Number 1 is that you can think about a problem systematically and then solve it systematically step by step too. And the number 2 is that you can envision the different inputs and outputs and edge cases for your problem. Because programs, when you put them out in the wild as part of software, can encounter any kind of inputs. And as you have thousands or millions of users, you will encounter any and every possible input. And often this has many security implications. It can take down the server, it can take down your application, or you can have a loss of data or loss of property. You can communicate your ideas clearly to coworkers. That's a very important part of problem solving. And most importantly, you can convert your thoughts and ideas into working code. And the code should also be readable to other people. So it's not really the knowledge of specific data structures or algorithms that's tested in an interview, but it is your approach towards the problem. So you may fail to solve the problem, but you may still clear the interview, or vice versa. You may solve the problem and still not clear the interview. So in this course, we will focus on the skills to both solve the problem and to clear interviews successfully. So that's why you need to learn data structures and algorithms. So coming back to the problem at hand, now you've read the problem and you may have been thinking about it, and maybe you have some ideas on how to solve it, and your first instinct might be to just start writing the code for it. But that is not the optimal strategy, and you may actually end up spending a longer time to solve the problem due to coding errors, or you may not be able to solve the problem at all. So what we are going to cover here is a systematic strategy that you should apply in interviews or in coding problems, in coding assessments, or in general whenever you're faced with a problem like this. So here's the strategy that we will apply. Step 1, state the problem clearly. Identify the input and output formats. Step 2, come up with some example inputs and outputs and try to cover all the edge cases. Step 3, come up with a correct solution for the problem. It can be as simple as possible and state it in plain English. Step 4, and this is a step that is optional sometimes, implement the solution and test it using example inputs, and then fix any bugs in your first solution. In step 5, analyze the algorithm's complexity and identify any inefficiencies. And finally, step 6, apply the right technique to overcome the inefficiency, and then go back to step 3, which is come up with a new correct solution, which is also efficient. Then implement the solution and analyze the algorithm's complexity. So this is the technique that we will apply over and over for the course of 6 weeks to many different problems. And applying the right technique is where the knowledge of common data structures and algorithms comes in handy. So this is the method we'll be using. So let's jump into the solution. Step 1, state the problem clearly. Now you will often encounter detailed word problems and coding challenges in interviews. They will go on for paragraphs and paragraphs. For instance, here we're talking about Alice having a deck of cards and then shuffling them, putting them out on a table, talking to Bob, etc., etc., etc. The first step is to state the problem clearly and precisely in abstract terms, because computers don't understand people, computers don't understand cards, computers understand numbers. So in this case, we can represent the sequence of cards as a list of numbers. So a list is a basic data structure in Python. And the turning over of a specific card is equivalent to the accessing of the value of the number at a certain position in the list. For instance, if we think of this set of cards being represented by this list, you can see here that this list is sorted in decreasing order. Then turning over a certain card is equivalent to accessing that specific element from the list. So turning over card number 2, or as we say in computer science, card number 1, because this is card number 0. And this is one thing that you might want to get into your head as well, that whenever you're counting, always start counting from 0. Otherwise you may run into many off by 1 errors. So this is position 0 and this is position 1. So if you turn over the card at position 1, it is as good as accessing an element from a given list, which in this case will turn out to be 11. So these are the positions in the list starting from 0. And now what we have to figure out is how many elements do we need to access. So we need to access the minimum number of elements to get to a particular element, right? So the problem can now be stated as follows. We need to write a program to find the position of a given number in a list arranged in decreasing order. We also need to minimize the number of times we access the elements from a list. So we're finding the position of the given number 7, and the position in this case is 3. And we want to minimize the number of times we access elements from the list. So if we go in this direction, for example, we would need to access 13, 11, 12, and finally we discover 7. If we come from this end, we may discover 7, 6, 5, 4, and finally we may discover 7. So definitely coming from the left is better than coming from the right. But is that the best? That's what we're solving. Now, once we've defined the problem, and what you should do is you should try to write down the problem in your own words. And primarily this is for you to make it clear to yourself. Either speak it out loud to the interviewer or write it down in your own words make it as short as long as possible so that you clearly understand what's in it. And then come up with the inputs and the outputs. So there are 2 inputs here. There's the input cards, which is a list of numbers sorted in decreasing order. And then the second input is a query, which is a number whose position in the array is to be determined. And there is one output, which is position. And the position is simply the position of query in the list of cards. For example, 7 is at position 3, counting from 0, of course. And as soon as you've written the input and output out, you can now write what is called the signature of our function, which is a structure of our function without any actual code inside it. So now we can call it def locate card with cards and query, and the single statement inside it called pass, because a function in Python cannot have an empty body. You need to put in at least one statement. So you always put in the pass statement first because it doesn't do anything. There you go. So now we have framed our problem in abstract terms. And now we have a function signature to work with. Now, a couple of tips here. This is something that interviewers specifically will look for, but also in coding assessments, because your code is also shared with the company. So you may want to name your functions properly and think carefully about the signature. For example, here, you should not call your function F1 or func1 or F or something like that. It's better to call it locate card because that's what it is doing. And the similar thing is true for variable names as well. Use descriptive variable names. One, because it's good coding practice, and second, because as you work on the problem, you may lose track of what a variable represents. For example, if you call this A and you call this B, now 20 minutes down the line, talking about the problem, writing different lines of code, you may forget what A and B represent. So please call them what they represent, even if it can get a little long. And finally, if you're unable to come up with a function signature, if you're unable to come up with a simple description, then discuss the problem with the interviewer if you're unsure how to frame it in abstract terms. So keep that in mind. And this is really the first and most important step, which is clarifying the problem statement and stating it clearly. Do not start coding before you have done this. Otherwise, you may get halfway into the code and realize that you have not understood the problem at all. So step 2. Now we will come up with some examples, some example inputs and outputs, and our goal will be to cover all the edge cases. So before we start implementing a function, we want to have some examples so that once we implement it, the first thing we'll want to know is it correct? And in general, the answer is no, because coding, especially when you're getting started, is hard because you have to think about many different scenarios. So, and especially interviews or coding assessments are also stressful situations. So you may not be able to focus and think about all the different things that you need to keep in mind. So simplest way to reduce the risk of going wrong is to use test cases. So here's one test case that we came up with. what we've done is we've taken the information that we had listed above in the inputs and outputs, and we've written it in as code. So now we have a variable called cards, which is a list of cards, a list of numbers. Then we have a query, which has the value 7. And then we have the output, which has the value 3. So the expected output from the function is 3. And once you have a test case, you can test your function at any point, anything you want to test. You can simply pass the input, for example, cards and query into the locate card function and get back a result. And you can see here right now, because there's nothing inside the function, the result you get back is none. But later you'll start getting back a proper result from your function. And what you can then do is you can compare the result with the output of the test case. So in this case, when we compare them, obviously the output is 3, the result is none, we get back false. Now, one thing we will do in this course to make testing easier, because we will be testing our algorithms again and again as we keep improving them, is that we will represent our test cases as dictionaries. So here, for example, this test case will be represented, or every test case will be represented as a dictionary containing 2 keys, input and output. And the input will contain 1 key for each argument to the function. So if your function arguments are called cards and query in the function signature, and that's why we wrote down a function signature first, so that we don't get confused here. So if your function arguments are called cards and query, then we can take one key called cards and put the value of cards there, 1 key called query, put the value of query there, and then in the output we simply put the output that we expect from the function. And now you can test this function like this. So how you might want to test it first is maybe by actually passing values like this. So you have test input cards and then test input query. But there's a trick here. Whenever you have a dictionary, so here we have a dictionary with 2 keys, and we want to pass these 2 keys as 2 arguments to a function. So we want to pass cards as the cards argument to the function locate card, and query as a query argument to locate cards. What you can do is you can simply put the dictionary itself and just write star star. Now, if you write star star, what Python does is it takes the keys from this dictionary, and the values are then used as arguments for parameters with these names. So there we are now calling locate card on test input, and we can compare it with test output, and you can see that we get back false. So that's one test case for us. But is that enough? Is that enough for you to now start writing code? Probably not, because out in the wild, your function should be able to handle any number or any set of valid inputs that we pass into it. And here are some possible variations that we might encounter, and it really helps to list them. In fact, while I was writing these variations, I realized that there are many cases that I had not thought of. So even after coding for 12, 15 years almost, I still find it really useful to list out all the scenarios that we can find our input in. So the simplest scenario is that the query occurs somewhere in the middle on the list of cards. This is what you imagine when you read the question. This is what is called the general case. But then there are some special scenarios as well. What if the query is the first element in cards? And what if the query is the last element in cards? What if the list cards contains just one element, which is the query itself? Or, and this is something that I had not thought of, what if the list cards does not even contain the number query? What if Alice is bluffing? So what should be Bob's strategy then to figure out that the number does not exist? What if the list of cards is empty? And what if the list contains repeating numbers? This is again another interesting thing that may not come to mind, because we said a list of numbers and we did not specify that the numbers are unique. So the list can contain repeating numbers. And finally, what if the number, the query itself, occurs in more than one position in cards? So those are 8 cases that I could think of. And just see if you can think of any more variations. And it's likely that when you first heard the problem, you did not think of all these cases, because you often tend to just focus on one generic case. It's hard to hold too many cases in mind, and that's why it helps to list them down, actually write them down. In a coding interview or in a coding assessment or an interview, you may want to put this in comments. If you have a coding page, you can just create a comments and list out all the test cases. And some of these, especially things like the empty array, or query not occurring in cards are called edge cases because they represent rare or extreme examples. And while edge cases may not occur very frequently, your program should be able to handle edge cases. Otherwise, they may fail in unexpected ways, or somebody with malintentions can use the edge cases to hack your software. So let's create some more test cases for the variations that we've listed, and we'll store all our test cases in a list for easier testing. So here we are creating a list called tests, and this time we will create all our test cases in the format that we discussed, which is a dictionary format, and we will keep appending them to our list. Now, if you do not understand lists and dictionaries and appending, then you can go back and review some of the basic material on Python, which is linked at the top of this notebook. So first we take the one test case that we already have, we put that, and we take maybe one more example of the query occurring somewhere in the middle. So here you can see this is the cards list, and then the query 1 occurs somewhere in the middle, although it's closer to one end. Then here's one case where the query is the first element, 4, and the output, obviously the output expected is 0. Here's one case where the query is the last element, minus 127. And this is another thing, the numbers could be negative as well, something you may want to keep in mind. Here's another one, where cards contains just one element, the query itself. Now, the problem does not state what to do if the list cards does not contain the number query. And you may often face these questions where it may not be clear what to do in a certain situation, or if a certain situation can occur. And when you have questions like this is a process you should follow. Step 1, read the problem statement carefully, or ask the interviewer to repeat the question. So read the problem statement carefully, and you will often find hints, and sometimes these hints are just single words somewhere. Often you will also find some examples provided with the problem. You will also find, if you scroll down to the bottom, you will find some conditions. You will find limits on what the numbers can be, whether they can be integers or can be decimals, whether they can be negative or positive. So it's important to read the problem carefully before you start coding, and look through the examples. And then ask the interviewer, or maybe post a question on the platform for a clarification. Often it happens that interviewers, because they take so many interviews, they may forget to specify a certain detail, or they might expect you to ask the question, because you should not be coding with an insufficient requirement. So to clarify the specifications of the problem is very important. So if you have any doubt, ask the interviewer, even if you are somewhat sure about it but just want to verify. It's a good idea to ask. Then finally, if you are done with all of these and you still do not have a solution, then you just make a reasonable assumption, state it, and move forward. So we will assume that our function will return -1 in case cards does not contain query. So if cards does not contain query, then we expect the function to return -1. Now here's one other case where the cards array is empty, and obviously then it does not contain the query as well. And finally, there's one last case, which is the number itself can repeat in cards. Numbers can repeat in cards, and then the query itself can repeat in cards. So here the query does not repeat, 3 does not repeat, but the numbers in the cards array do repeat. And the last case is when the query itself repeats. So you can see here in cards, the query occurs many times. Once again, it is not specified what to do here, and sometimes it may be okay. Sometimes the problem statement may just say that return any one position, but more likely than not, what you will want to do is you may want to make it more deterministic, and that will also make it easy for you to test the function. So what we can say, we can impose this additional restriction that we will expect our function to return the first occurrence of query. And that will make it easier for us to test, so that when we're testing our problem, we know that if we're getting a failure, it's not because of multiple possible answers, but it's because of some issue in our code, right? So you want to get good feedback from failures, and that's why you want your tests to be deterministic. So here is the final test. And now we can see the full list of test cases. So now we can see the list of test cases here. So you have about 8 or 10 test cases here. You may not need to create this many test cases in an interview or a coding assessment, depending on how much time you have, but you should create at least a few, at least cover the 3 or 4 edge cases. A good number to aim for would be 5. And this will not only help you in the coding interview, help you solve the problem, this will also be appreciated by the interviewer because it shows that you're thinking about the problem. So definitely take a minute or two. We've spent 10-15 minutes talking about this, but once you start applying this technique over and over, you will see that you will start creating test cases in seconds. So as soon as you read the problem and you state the problem, find the input format, find the output format, write a function signature and write the test. Then you will start working on test. The ideas will automatically start coming to you. And within maybe 2 or 3 minutes, you will be done with both of these steps. So great, we now have a fairly exhaustive set of test cases, and creating test cases beforehand allows you to identify different variations and edge cases. And sometimes it may happen that you may have no clue how to work on the problem. You may feel completely confused, but if you simply start writing multiple test cases and start looking at them, like literally just staring at the test cases, the question and the answer, the solution will reveal itself to you. So don't underestimate the power of writing things down. And don't stress out if you can't come up with an exhaustive list of test cases, because this takes time. It's a skill that you cultivate with time. So what you can do is you can list out maybe the test cases that come to your mind right now and put them in a single place and keep coming back. Whenever a new test case comes to mind while coding or while discussing or while analyzing, you can just come back to the same place and write down the test case. The important thing is that you have a single place where you're listing all test cases. So we've written our test cases now. And now we can come up with a correct solution. And how do you come up with the correct solution? Not by writing code, but by first stating it in plain English. So your first goal, and by correct, we do not mean the best or the most efficient solution. First, we want to solve the problem. We want to figure out where the particular number lies in the list and not to minimize, because that's solving two problems at once and sometimes that can get tricky. So first aim for correctness, then aim for efficiency. And the simplest or the most obvious solution, which almost always exists and is almost always very easy to see, involves checking all the possible answers. And this is also called the brute force solution. So in this problem, coming up with the brute force solution is quite easy. Bob can simply turn over the cards in order one by one till he finds the card with the given number on it. So this is how it might work if we want to implement it in code. And this is where writing it in your own words becomes important. So we create a variable called position inside a function with the value 0. Then we check that the number at the index position in the card list equals query or not. Now, if it does, since we're starting from the beginning, if it does, then position is the answer and we can return it from our function. But if it doesn't, then we simply increment the value of position by 1 and then we repeat the steps. So we go back to step 2 and when we check whether the number at the index position in cards equals query. And once again, if it does, we return position. If not, we increment the position once again and repeat. And we repeat that till we reach the last position. And if the number was not found, we return -1. So it's a simple 4-5 step description. Doesn't take very long. You can either say it out loud to the interviewer. They will also appreciate it, that they will know, you may know that you know the brute force solution and you may not say it because it seems too simple or obvious, but the interviewer doesn't know that. So it's important to state the brute force solution. You may say that the brute force solution is fairly straightforward and it goes like this. Steps 1, 2, 3, 4, it just takes 30 seconds. But at the very least, it informs the interviewer that you're able to think of some solution. And it happens very often. I've seen it in interviews where 30-40 minutes have passed out of 45 minutes and not a single solution has been proposed so far, even though many lines of code have been written. So it's important to state your solution. And if you state your solution, the interviewer will also help you and correct you as you go forward, right? So it is a collaborative experience. It is a discussion. So use that. And if you are in a coding assessment, you may just want to write out a few comments. And what we've implemented here is, congratulations, is just our first algorithm. And an algorithm is simply a list of statements, a list of steps that can be converted into code and executed by a computer on different sets of inputs. So this particular algorithm is called linear search because it involves searching through a list in a linear fashion, element by element. So now we're ready to implement the solution. And just a quick tip, as I've already said, always try to express the algorithm in your own words. And it can be as brief or as detailed as you like. And don't underestimate the power of writing. Writing can be a great tool for thinking. It's likely that you will find that some part of the solution is difficult for you to express. And that simply suggests that you are probably unable to think about that part clearly. So the more clearly you're able to express your thoughts, the easier it will be for you to turn it into code. And you will not have to come up with a strategy while you're writing the code. So you can focus on coding and focus on avoiding errors. And that brings us to the next step. Implement the solution and then test it using the example input. So now you can see how everything comes together. We've already know what the function signature looks like, what the inputs look like. We already have some test cases, and through the test cases, we've also identified what are the different edge cases we need to handle. And we've already written out a description, a rough description of what the algorithm looks like. And in fact, what you can do is you can simply write out comments within your function as the English description, and then you simply need to fill out code for those comments. So for instance, here are the 5 steps that we had just written down. Create a variable, position with the value 0, set up a loop, check if the element matches the query. If yes, the answer is found. If not, increment the position and then go back and then check if we've reached the end of the array. If we have, then we return -1. So, and the code now is pretty straightforward. Now we create the position variable 0. We set while true. So while true kicks off a loop, and we just want to first set up a loop and then we can break out of it when we need to. Then we check if the element at the value position matches the query. If it does, we return the position. If it doesn't, then we come to this part. If it does, then the function exits and none of this code gets executed. But if it doesn't, then we increment the position. And then we check if we have reached the end. Now, if we have reached the end, obviously we don't want to continue. So we can simply return -1 and exit the loop and exit the function itself. But if we have not reached the end, then we go back to the top of the loop and now position starts out with value 1. So we check value 0, 1, 2, 3, so on up to the end of the array. Simple enough. Great. So now we have our first function and let's test our function with the first test case. So here's our test case once again, and we can simply call locate card with the test input and the cards in the query. And this is the result we get. And you can already see that the result matches the output. And that's why when we compare them, we get the value true. So yeah, the results match the output. And because this is something that you should be doing very often, in this course, we have put together a small function for you within the Jovian Python library. So the Jovian platform also offers a Python helper library that contains some utility functions. So we've put together a small function for you called evaluate test case, and you can write it on your own as well, but you can use this library version. So let's install the library. We will install the Jovian library using pip install Jovian -- upgrade. And then from jovian.python DSA, so Jovian is the name of the library. And then inside the Jovian library, since we have many courses, the Python DSA course, the utilities for this course are present inside the Python DSA module. From that module, we import the function evaluate test case. And finally, we can call evaluate test case, and then we can give it the function that we want to test. So we want to test the locate card function and the test case. The test case needs to be defined in this format. So all it is going to do is it is going to pick out the input, pass it into the function, get the output, compare that output with the expected output, and also print some information for you to see. So here's what it does. It prints out the input. It prints out the expected output. It prints out the actual output. It prints the execution time. And this is something that will become important later, and it tells you whether the test has passed or not. So it's nice to have this, because so we don't have to look through the output and input and compare them, especially when you're in a situation where you need to think fast. It's helpful to create a small function that can just print pass or fail for a test case. So now, while it may seem like we have a working solution because our test case has passed, we can't be sure about it until we test the function with all the test cases. So for doing that, we can use the evaluate test cases function. So just as you have evaluate test case, you have evaluate test cases, also part of the Jovian library. And you can call evaluate test cases with the same function locate card, and this time pass it a list of test cases. Each of the test cases is a dictionary. Again, you don't have to use this function. You can simply put things into a loop. So you can always just do for test in tests and then simply call evaluate test with locate card and test. Or you can even just directly call locate card with the test inputs and the test out, and compare the output with the test output, right? So you can do this as well, and you can simply print that. So here's a simple way to do this, what we are doing here. But what we'll do is we'll use the evaluate test cases function because it prints out a lot of useful information for us. So now you can see that it prints out case by case. Now test case 0, we have input, expected output, actual output, the test case has passed. That's what we saw. In fact, it's the same test we just did. Test case 1 passes as well. Test case 2 passes. Test case 3, 4, 5, 6. Okay, all of them are fine. Okay. Test case 6 seems to have caused an error. So here is the error. It says list index out of range. So that's okay. It's perfectly all right for your functions to encounter an error. So the first thing, the most important thing is not to panic. In fact, it's a good thing that we know exactly where the function is failing. If you look back here, you can see what the issue is, and then we'll see how to fix the error. But one good strategy to approach this is to keep in mind that there will always be bugs in your code, and approach writing code not with the assumption that your code will be correct, but go with the default assumption that your code will be wrong, that there will be issues. What that lets you do is, one, you do not feel demotivated or you do not panic when you see an error. And second, you then tend to be a little more careful while actually writing the code. So the way you should be writing code is every time you write a line of code, you should be asking yourself, how can this line of code go wrong? Or in this particular case, how can cards position equals query in an if statement go wrong and throw an error? And let's look at it. One easy way to check this is to add what is called a logging, or what is called printing the information inside a function. So we'll just rewrite our function. In our locate card function, we will put in cards and we will put in query, the exact same function that we have. We'll set the position. But before we create the while loop, we'll simply print the cards in the query. So just for our information, just so that we can see what the function is working through, we can get some visibility into the function. We print out cards and query, and then while true. So this is the same loop. At the beginning of the loop, we will print out the position that we are tracking. Okay, so let's do that. We've simply added some print statements, and this print statement will give us an insight into the inner working of the function. Now, if you do not put in a print statement, then you will have to work it out yourself by reading the code and executing it in your head. It's always easier to just print all the information and then print it nicely. Just say cards and query. We could also have done this without saying cards here, but then that would make it a little harder to read. Then that would be more cognitive overload, apart from already dealing with the stress of solving an error, right? So just add nice, pretty print statements to make it very obvious what we are printing. So let's see now. Let us get the test case out. So let's get from test 6, get the input, get the cards, get the query as well, and pass it into locate card. And now we see that initially the cards array is empty, and the query is 7, and the position is 0. And then we encounter an error. We encounter the error list index out of range on the line cards position equals query. And now at this point, it should be fairly obvious what the issue is. The issue obviously is that we have an empty list. An empty list has no elements, but we're trying to access the position 0, which is in normal human conversation, the first element of a list. But there is no first element to access, and that is why we get the error list index out of range. So this is very important. Whenever you get an error, do not try to start looking at the code first. Just try to understand the error first. And if you're unable to understand the error, just add some print statements. There are tools like debuggers that people use, but I personally in 15 years haven't used a debugger. I maybe used it a couple of times, but I don't know how to use it. Print statements are really simple. You just put them in, chuck them into the function wherever you need them, as many print statements as you need with nice clear messages, make it very obvious. And that will almost certainly solve the issue for you. So the cards array is empty. We cannot access position 0. So what's the solution here? The solution obviously is that before we access anything from a list, we need to make sure that we can access that list. And this is the way to do it. So now we've rewritten our function slightly. We once again start out with position 0, but this time, instead of putting in a while true, instead of assuming that we can access the 0th element of the list, we say that the position should be less than the length of cards. Now, if you have a cards list of n elements, the indices go from 0 to n minus 1. Or in the case of 0 elements, there are no indices to access. So the position has to be less than the length of cards for you to be able to access it. And in this case, the length of the cards will be 0. So 0 is not less than 0. So the while loop will not run at all, and we will directly return minus 1. But if the card does have elements, then we can check the element at the value position, compare it to the query, and return the position. If it does not match the query, we can increment the position. So that was a fairly straightforward fix, easy save. So let's test the failing case again. Great. So looks like the failing case is now passing because we have output -1 and the expected output matches the actual output of the function. -1 because the query does not exist in the array, which is empty, of course. Now this is not enough. It is every time you make a change to the code, you want to go back and test all the test cases, because what may happen is while fixing one error, you may introduce another error. And that is where having a good set of test cases is very important. So let's run evaluate test cases once again. You can see here this time that all the test cases are passing. And it's just nice to, it just makes you feel good as well, makes you feel motivated as well to see that a bunch of test cases are passing. Now, in a real coding assessment or a real interview, you can probably skip the step of implementing and testing the brute force solution in the interest of time, because it may take about 5 to 10 minutes to implement the solution. And then if you have errors in the solution, it may take some more time to fix those errors. So it's generally quite easy to figure out the complexity, which we'll talk about in a second, of the brute force solution from the plain English description. And that is why you should first state it in plain English, which only takes around 20 seconds or so, and the computer doesn't throw errors at you for speaking. So you can just state the plain English description and move on, talk about the complexity and start optimizing it. But while you're practicing, always implement the brute force solution too. And there's an important reason why you should know how to implement the brute force solution, because in case you're not able to figure out the optimal solution to the problem, you can still go back and implement the brute force solution. And in a lot of cases, that's okay. Sometimes interviewers ask hard questions just to push your boundaries a little bit. But if you're unable to figure out the optimal solution, then they will allow you to implement the brute force solution. So that is why you should state it, and that is why you should know how to implement it. Okay, so we're done now with the implementation of our brute force or simplest solution. And now we need to analyze it. And this is where we'll now learn about what is called the complexity of an algorithm. What does it mean? Now recall the statement from the original question. Alice challenges Bob to pick out the card containing the given number by turning over as few cards as possible. But right now what we're doing is we are simply turning over cards one by one. And before we talk about what does it mean to minimize the number of times we turn over cards or the number of times we access elements, we need a way to measure it. And let's think about it. It's as simple as just thinking about it. Since we access the list element once in every iteration, so here's our code. Our code is pretty straightforward. And this is where we are accessing an element from the list. So since we access the element once in every iteration for a list of size n, we access the elements from the list up to n times, because we may have to access this element and then this element and this element and so on. So Bob may need to overturn up to n cards in the worst case to find the required card. Now let's introduce an additional condition that suppose Bob is only allowed to overturn one card per minute. So that means it may take him 30 minutes to find the required card in the worst case, if 30 cards are laid out on the table. Now, is this really the best he can do? Or is there a way for Bob to arrive at the answer by turning over just 5 cards and save 25 minutes instead of turning over all 30? And this field of study, and by the way, Bob in this case is a representative of what a computer does. And a computer takes some amount of finite time to perform each instruction. So each array access actually takes some time, although it's so fast that we do not see it, especially for small inputs. But this is something that will become increasingly important as we go week over week, where we'll see that we will start to see the limits of how long it takes computers to solve certain problems. So the field of study concerned with finding the amount of time or the amount of space or the amount of other resources required to complete the execution of a program is called the analysis of algorithms. And the process of figuring out the best algorithm to solve a problem is called algorithm design. And that is what we are doing here. We are actually doing the analysis of algorithms right now and algorithm design next. So there are a couple of terms we need to understand, and then we'll go back to writing code. First thing is complexity, and the second thing is the big O notation. And both of these are terms that you will hear very frequently when you're talking about data structures and algorithms, when you're talking about coding interviews, assessments. So these are terms that you need to understand. And they're fairly simple terms, although the term itself is complexity, but all it means is that the complexity of an algorithm is simply a measure, some measure of the amount of time or space required by an algorithm to process an input of a given size. Example, if you have a list of size n, then the complexity is the amount of time required or the amount of space required on the RAM to process an input of that size. Now, unless otherwise stated, the term complexity always refers to worst case complexity. So it's possible that the Bob turns over the first card and that is the answer, but we always talk about what is the longest or the highest possible time or space that may be taken by the program to process an input, right? So we need to design our programs keeping the worst case in mind. Now, in case of linear search, which is what we've implemented just now, the time complexity of the algorithm is some constant C times n, assuming n is the size of the list, n is the number of cards. Right. So now this constant C obviously depends on the number of operations that we perform in each iteration. So in each loop, for example, we have 4 to 5 statements, and then the time taken to execute a statement on your specific hardware. Now, if you have a 2 gigahertz computer, that may be twice as fast as a 1 gigahertz computer. If you're running it on a phone, it may be different. So the C captures all of these things. So information about the number of specific operations that we perform in each iteration and information about the actual hardware that you're running on. So Cn is the time complexity and n is the size of the input. So in some sense, what we understand from this is that the time complexity is proportional to the size of the input. And that's the important part here. The constant, it doesn't change. As you change the input, the constant doesn't really change. Now, similarly, the space complexity. Now, since we are already given an array, the additional space that our linear search requires is simply a single constant when we are calling it C prime or C dash, and it is independent of n. So no matter how large a list is given to you and the list is already present in memory, we just need to allocate one new variable called position, and that variable is used to iterate through the array, and it occupies a constant space in the computer memory because we go on updating the variable, right? So the space complexity is C or constant. It is independent of n. Now, what we do normally is to represent the worst case complexity, we often use the big O notation. And in the big O notation, what we do is we drop any fixed constants and we lower the powers of and we drop any fixed constants and we drop any lower powers of variables. So the idea here is to capture just the trend of the relationship between the size of the input and the complexity of the algorithm. For example, if the time complexity of an algorithm is some constant times n cube plus some constant times n square plus some constant times n plus some constant, where n is the size of the input, in the big O notation, we simply say that it is order of n cube, which is that, in the long run, if you just study the trend, the trend will be something which looks a little bit like the n cube function, and it may be offset by a constant or such. So Putting it this way, the time complexity of linear search is order n because we just drop the constant c, and the space complexity is order 1. So we again drop the constant c prime. And we'll see why it's okay to drop the constant. Sometimes you may find that, okay, we're not exactly doing n iterations, but we're doing n minus 1 iterations. So we drop the -1. Sometimes you will find that we are just doing n by 2 iterations, and that's simply half of n. So we drop the half. And you might wonder that, okay, that might take twice or 3 times the amount of time. Why are we dropping that constant? Because that's probably an important thing to keep in mind. But we'll see soon as we implement our efficient solution to the problem. So before we move forward, before we optimize the algorithm, we are just going to save our work, because this notebook, as I mentioned to you, is running on an online platform. We've set up everything for you. You've not had to install anything, but because thousands of people are using this platform, this will shut down. This will not keep running forever. And what you need to do is you need to save your work from time to time. And here is how you can save your work and then pick it up. Everything happens on the Jovian platform. There's no need to download anything. Although you could download it if you want, but there's no need to download anything. So all you need to do is use the Jovian library. Once again, we've got another helpful function for you. So you say import Jovian and then run jovian.commit. So you run jovian.commit and then give it a project name, the project name by which you want to identify this specific notebook. And then there are some other arguments. This is not too important. So you can even skip this and that should be perfectly fine. So now when you run jovian.commit, we will capture a snapshot of your notebook from this online platform or wherever it is running. Even if you're running it on your own computer, we will capture a snapshot of your notebook from your computer, wherever it's running, and we will upload it and give you a link where you can access it. So let's open up this link here. So now you will be able to see this page called Python binary search, and it will be on your profile. And you can scroll down and see that it contains all the explanations and it contains all the code. So this is a read-only version of the Jupyter Notebook. So the read-only version of the Jupyter Notebook obviously does not require us to keep servers running so that you can run this code. And when you need to run it, your work is saved to whatever extent you have executed things. And now when you need to run it, you simply click run and then click run on binder once again. Okay, so and that is how you resume your work. So what this will do is this will set up a new machine for you, and on the new machine it will post the Jupyter Notebook, and it will start up the machine for you, open up the Jupyter Notebook, and you will be able to start running the code. And not just you, now you can make your notebooks public or you can keep them private. You have multiple viewership options. So you have public and private, not just you, but anybody else. So you can take this link and tweet it out. If there's an interesting problem that you worked on, you want to tweet it out, you can just share this link online and anybody will be able to read through your solution and they can run it as well, right? In fact, the notebook that I've shared with you is hosted on my profile. So Jovian is not just a platform for you to learn. It's also a platform for you to build a repository of projects. Now, if you go back to your profile, you click on your profile or click on the Jovian logo, and you can see here that you will find a notebooks tab. And in the notebooks tab, you will find all the notebooks that you have worked on in the past. Okay, so anything that you have committed using jovian.commit, you will be able to resume working on it. So that's how you save your work and keep saving your work from time to time. All you need to do is run jovian.commit. You do not even need to put in this project argument. This is just something if you want to actually give your project a name. Otherwise, the name will be picked automatically. So just keep running jovian.commit from time to time. Especially if you're leaving your computer for half an hour or so, and your computer goes to sleep, then the server will shut down and you may lose your work. Coming back to our problem, we've just implemented linear search and we understood that it has the complexity of order n, and that's why it's called linear. It runs in a linear time is another expression that is used. It is also called linear because we are going through the array step by step. Now, the next step is to apply the right technique to overcome this efficiency. Now, of course, we've not learned any techniques yet, but we can probably figure it out if we think about it. And maybe this is something that occurred to you right at the beginning. And the idea that occurred to you is something that we will now implement. So at the moment, we are simply going over the cards one by one and not even utilizing the fact that they are sorted. And that's why our approach is pretty poor. We're basically checking everything So it's not a great solution, but it would be great if somehow this would be the best case. If somehow Bob could guess the card at the first attempt, that would be perfect. Then that would be an order one. That would be a constant time solution. But with all the cards turned over, it's simply impossible to guess the right card. Now the next best idea is to maybe pick a random card. So maybe let's say Bob picks this card and this card turns out to be a 9. Now Bob can use the fact that the cards are in sorted order. So if this card turns out to be 9, that means all of these cards have numbers greater than 9 and the target card is 7. So the target card cannot lie in this region. So the target card has to lie in this region. And just by picking a random card rather than picking the first card, Bob has eliminated 4 out of 7 cards to be checked, right? So with one check, Bob has eliminated a total of 5 cards, 1, 2, 3, 4, 5. And of course, if this number turns out to be 7, perfect, great guess. But even if it doesn't, we've still eliminated quite a few. If this number turns out to be less than 7, we've still eliminated 3 cards. So that's the basic idea here, that we pick something not from the edges, but somewhere in the middle. Now, what is the best place to pick something in the middle? Now, obviously, when we are picking a card, we do not know whether it is going to be less than or greater than the number that we want, especially when everything is close. So it's best to just pick the middle card so that whichever case turns out to be, we're still left with at most 3 cards to process, right? So if you pick this card and it doesn't turn out to be 7, you either need to look at these 3 or you need to look at these 3. So that is the strategy we'll follow. And this technique is called binary search. And why do it just once? Just keep repeating it. So each time you pick the middle card and you can eliminate half of the array. And this is what the strategy looks like. So here we have the array. And in the array, we want to figure out the number 6. So this is a slightly different problem, but still decreasing order. We want to figure out the number 6. So we access the middle element. Okay, we compare it with 6. Now it is not 6. Okay, it was a bad guess, no problem. But we know that 4 is less than 6. So that means that 6 lies to the left of 4. So we've suddenly eliminated half of the array. We've done one access and eliminated half of it. And now we're left with 3 numbers. We pick the middle number. We get 7. 7 is greater than 6. That means the number lies on the right. Now we're left with just one card. We overturn that last card or we check that last number. Okay, it is equal to 6. Great. If it is not, well, nothing more left to check. All the numbers here are greater than 6, are less than 6, and all the numbers before this are greater than 6. So if this number isn't 6, then there's no 6. And just like that, for an array of 7 elements, we have done just 3 checks and arrived at the answer. And that was the worst case, right? It will never take, you can verify that it will never take more than 3 checks. If 6 comes at this position, we guess it immediately. If 6 comes at this position or this position, we guess it in 2 checks. And then if 6 comes at any of the other positions, we will guess it in 3 checks. So that's pretty good. And now the idea, if you read this part, it says, apply the right technique to overcome the inefficiency and then repeat the steps 3 to 6. So now we're going to go back to step 3, which was come up with a correct solution for the problem and state it in plain English. And we have come up with a solution already. We just need to state it. So here is how this technique called binary search is applied to the problem. It's called binary because, well, we take a left and right decision. So first we find the middle element of the list. If it matches the queried number, then we return the middle position as the answer. And if it is less than the queried number, then we search the first half of the list. And if it's greater than the queried number, then we search the second half of the list. So the exact thing that we saw here, we apply it here. And finally, if no more elements remain, we simply return -1. So let's just save our work. Now from this point on, we'll keep saving our work from time to time using jovian.commit. So now we've come up with the algorithm, and you can, again, it's important to write it in your own words, whether you want to write a short description, a paragraph, or a step-by-step guide, but write it in your own words, and you'll do this in the assignment. So let's implement the solution now and test it using the example inputs. So here's the implementation. So what we'll do is we will look at, once again, let's go back to this visual representation, and we will keep a track of our search space. So initially our search space is the entire array. So that means we have an array of 7 numbers. So our search space goes from position 0 to position 6. And slowly we'll keep reducing our search space over time. So to keep track of the search space, we'll create 2 variables, low and high. Low will have the value 0, which is it will point to the first position in the array, and high will have the value pointing to the last valid position in the array, which is len cards minus 1. So while low, and then the while loop becomes very simple, because as long as we have at least one element in our search space, we can go ahead. Now, to have at least one element in our search space, the low value, which is the starting index, should be less than or equal to the end value, right? So while low is less than or equal to high, because if the starting index is higher than the end index, basically we've exhausted and we've covered the entire list, and there's nothing more that we can search for. So we should exit at this point. Okay. So now once we have, once this condition is satisfied, and it is initially, let's say you have 7 cards, low is 0, cards is len cards minus 1 is 6. Then you find the middle position, and you can get the middle position by doing low plus high divided by 2. And now let's start applying that strategy here, where we say that every time we write a line of code, we should think about how it can go wrong. Now, if you write it like this, low plus high divided by 2, and think about how it can go wrong. Okay, low plus high may not be divisible by 2. And if low plus high is not divisible by 2, you may end up with a decimal number. Now, if you do end up with a decimal number, and in fact, the division operator in Python always retains a floating point number, then you cannot use it as an array index, because we want to use this as a position within the array. So that's why we need the double slash, which is the integer division, which simply returns the quotient. So we get the middle position, and then we get the number at the middle position. So we also get cards mid. So we access that element from the array. Now this is where it makes it easy for us to count the number of times we access, because here is one access happening inside the list and there are no other accesses. Then we get the mid number. And remember, last time we faced an error and we had to add print statements. You might as well just add print statements right away. So here's what you can do. We can just print the value of low, the value of high, the value of mid, and the value of mid number. What this will do is this will help you check whether the number is working as expected, whether the function is working as expected or not. So now here comes the actual check, the meat of the problem. If the middle number matches the query, then we return the middle number. Great. We found it. Well done. Now, if the middle number is less than the query, now remember the elements are in sorted array and we are looking for the number query. Now the middle number is less than the query. So that means the query probably lies to the left of it, because the elements are in decreasing order, right? So if the query lies to the left of it, so then we need to decrease the search space from the beginning to the position just before the middle number, right? So what we can do is we can simply set high to mid minus 1. On the other hand, if mid number is greater than query, so that means because of the decreasing order of the array, the query lies to the right. Now we need to move the starting of the search space to beyond the middle number. So we simply set low to mid plus 1, and that's it. And you can see that we've used a if elif loop here. So elif stands for else if in Python. And here the last condition might as well just have been else, because there are only 3 possibilities. Either they're equal, or mid number is less, or it's greater. But sometimes it's nice to list out all possibilities just to make it super clear, and it makes it easy for you while debugging, fixing issues as well. Okay. So that's our binary search based algorithm. And finally, when we exit out of the loop, if you have not returned the middle number, if you have not exited the function yet, then we return -1, that the number was not found. So let's test it out using our test cases. And we have our handy evaluate test cases function here, but you can also test it manually if you want by passing individual test cases, but I'll just do this from now on. So great. So now we have test case 0. This is the input and this is the query, and it passed. Here we have test case 1, this is the input and this is the query, and it passed. And now because we have these print statements, we can clearly look into our test cases and actually tell if this is tested correctly or not. Because now you can see here that we started out with low 0, high 7, and a mid value of 3. So 0, 1, 2, 3, we found the number 7. The query is 1. So we need to check this half of the array, and that's exactly what we did. We moved low to 4 and high remained 7. Then mid number became 3. So that means once again, we need to check this half of the array, and then we check this number, and then we found the output. So now you can see exactly how the algorithm works. And this is in general what you want as a programmer. You want to have a full understanding of the code that you've written. You don't want your code to work incidentally. You don't want to be in a position where you are just fixing things, you're trying out different things, and somehow at once the code works. You want to be in complete control. You want to know that this is exactly what the code is doing, and if it is failing, why it is failing. So we go to test case 2, 3, 4, 5, 6. Looks good. Looks like we may have solved everything. Probably not. So test case 8 seems to have failed. So test case 8 is this number, this list, and this list contains repeating numbers, and not just repeating numbers, but the query itself occurs multiple times. And now if we look here, and maybe let's go down and evaluate just the test case separately. So here we are now using the singular version of the evaluate function. So if you look here, you can see you have 8, 8, 6, 6, a bunch of 6s, then 3, 2, 2, 0. The query is 6. So we start out with a low of 0, high of 14, total of 15 elements. That gives you a middle position of 7 and the mid number at that position. So let's count 0, 1, 2, 3, 4, 5, 6, 7. Okay. And the mid number at that position is 6. Great. 6 is also the query. So that's why our function returns 7. But remember that we had decided that our function should return the first position of the number within the array. So our function is failing that condition. And why is that happening? Because unlike linear search, where we start from the left, and so we'll always bump into the first position because of the decreasing order of elements. So we'll encounter this 6 before we encounter this 6. Binary search does not access elements in an order. It accesses elements sort of randomly. There's still a strategy, but it goes left and right, and it also depends on the values of specific elements. Whether this element is accessed before this element can depend on the value of, let's say, this element, right? So as such, it's kind of a pseudo-random kind of order. And so we need an additional condition to keep track of it, right? So how do we fix it? So the way to fix it is actually quite simple. When we find that the middle position in a particular range is equal to the query, we simply need to check whether it is the first occurrence of the query in the list or not. That is, whether the number that comes before it, is it equal to query or not? If the number that comes before the middle element is also equal to query, then obviously the middle element is not the first occurrence. So that simply means that we can go back, and because it can occur multiple times before, that simply means that we can now search the left half. On the other hand, if the number before the middle element is not equal to query, and obviously because it is a sorted list, it will be greater than query, then all the numbers here are going to be greater than the query, and and so this must be the first or the only position. Okay, so make sure you understand that this must be the first or the only position where the query occurs. So once again, to make it easier, what we will do is, because there is some logic involved here, what we'll do is we'll define a helper function called test location. And this is a very helpful thing that you can do every time you find that, okay, you have to cover these special cases and your function may start to get slightly longer and slightly more complicated. What you may want to do is create a helper function. And a good rule of thumb is not to have functions that are more than 10 lines of code or so. I try to keep my functions below 7 lines of code, because 7-8 lines is approximately the amount of information that you can hold in your head at once. So if your function is about 7-8 lines, you can probably take a quick glance and tell what it's doing, identify issues. But anywhere beyond that, it's very hard. And if you're writing functions that are going into hundreds of lines, please stop doing that. Please start breaking your code into small functions. There's a quote by, I forget who it is by, but he's a creator of, I think it's Eric Meyer. He created the RX library for reactive programming. And he said that great programmers write baby code, which is really small bits of code that anybody can understand with a single look. So you should be writing as many functions, as many small pieces of code, small pieces of logic as possible. So let's see a test location function. Its purpose is to take the query and then take just a specific position. So forget about binary search for now. Just take a specific position and tell if that position is the answer. And how do we do that? We first get the mid number from the cards. So we get a mid number from cards. So then we print out mid and we print out mid number. And then we compare the mid number with the query. So this is the special case that we need to handle. This is where we had the error. Now what we need to check is if the element before the mid number is also equal to query. So if the element before the mid number is also equal to query, then we need to go left. So just to make it super clear, what we'll do is instead of setting high, low, etc., we'll simply say that we need to go left. So we'll return the actual string left. But one thing to keep in mind here, because once again, whenever you're accessing an array, you need to make sure that the index is valid. So we simply check that mid -1 should be greater than or equal to 0, that mid is not this position, and which can happen as your search space decreases. For example, if this is your search space, your mid will actually be this position. So if it is equal to, if the number before the mid number is equal to query, then we return left. Otherwise we return found. Once again, making it very obvious that we have found the number, so we return found. Else, the other case is if the mid number is less than query, that means that the query lies on the left because of the decreasing order of the list. So once again, we need to search on the left, else it returns right. So a test location simply tells us whether we found the solution, or we need to look on the left, or we need to look on the right. Now, sometimes you will see programs, especially in C++, Java, return something like -1, 0, and 1, and then use that to represent whether you should go left and right. But Python is a high-level language, and strings are a first-class feature of the language. So just use strings because they are really descriptive. They make your code readable. Somebody else reading your code will be able to understand. Now, if you're looking at -1, +1, etc., that is going to be difficult for people to understand. So now we can simplify a locate card function. Once again, we have our low, high, len cards -1, 0, and len cards -1. The while loop is the same, and we print low and high as well. So we are printing low and high inside the locate card function, and then we are printing mid and mid number inside the test location function. Wherever is the right place to print something, you print it. Then we get the mid position, and now we simply call test location. So we are testing if mid is the answer, and if it is not the answer, should we go left or should we go right? Now that makes it really simple, because now we get this result and we check this result, and if it says found, then we return mid. That's the answer. If it says left, then we return mid -1, or then we simply move high to mid -1. And if it returns right, then we simply set low to mid +1. So we are simply changing the start position of the search space to after the middle element. And here we are changing the end position of the search space to before the middle element, right? So this makes it extremely obvious, and it's really hard to go wrong when you write code like this. Especially so when you have, and binary search problems are especially tricky because they always have these special cases that you need to handle. And if you start handling them within this if loop, so now you have a while loop inside which you have an if loop inside which you have another if statement, and it can get pretty tricky and difficult to debug. So let's evaluate that test case, and it looks like that test case has passed this time perfectly. You can go through the logs here to verify it. Let's evaluate the test case, all the test cases as well. We should do this every time we change the function. And that is why it's helpful to have a function where you can, every time you make a change, you can just run the test. And on a coding platform like LeetCode or HackerRank, you will be given some test cases, although those test cases will not be visible to you. So you can submit your solution, but you may not get an actual result. You may not get to know what the test case was or where your answer was wrong. And that's where you may want to create your own test cases if you're getting a lot of errors. And in fact, once you've written out the algorithm, you may realize that, okay, maybe you need to add more test cases. What if the number lies in the first half of the array? What if the number lies in the second half of the array? So this was not an important factor when we were not thinking about binary search. But now that we're thinking in this direction of splitting the array into half, we may want to add some test cases where the number lies exactly in the middle, in the left, in the right. And the simplest way to do that is now go back to the tests array. So you can create a new cell here by pressing the character B. So if you click outside and press the character B, you can create a new cell, and then you can simply do tests.append and then write your test case. So here is the final code for the algorithm without the print statements. So we have test location and then we have locate card. And try creating a few more test cases to test your algorithm more extensively. And once again, at every step, we are going to save our work by running jovian.commit. So now we're down to analyzing the algorithm's complexity and identifying inefficiencies if there are any. Now, you may have just read online, you can actually look it up, just search for complexity of binary search and you will find an answer. But and you may even just say that in interviews, but it's always nice to just come up with that answer from first principles. It's always nice, especially in an interview, if you can talk through it, if you can talk through why it is why it is whatever it is, and we'll see what that is. So now let's once again try to count the number of iterations in the algorithm, because we need to minimize the number of times we access elements from the array. And to do that, we know that in each iteration, we are accessing the element just once. And then we are comparing it. So we're doing a bunch of other operations, but in each iteration, we're accessing one element. So we need to count just the number of iterations, the number of times the while loop was executed. Now, if we start out with an array of n elements, then each time the size of the array reduces to half for the next iteration. Now, that's roughly true because when you check the middle element and then you decide whether to go left or right, it's actually probably n by 2 minus 1 if n is even, and if n is odd, it is the floor of n by 2. But again, with algorithms, with complexities, we are generally interested in studying the trend. So we can ignore that small part in the calculation. So let's say the important part is that even if it's okay to overestimate a little bit, but try not to underestimate. So after the first iteration, we may be left with a search space of size n by 2. It may be slightly less than that, but it's okay to overestimate. So we have n. So after the first iteration, we are left with a search space of n by 2. Then we split it into half again. So next time we may be left with a search space of n by 4, which is n divided by 2 square. And then we may be left with n by 8. And it's possible that at any of these iterations, we may just exit because we may have found the right number. But what we always try to analyze is the worst case complexity of an algorithm. What is the longest possible amount of time or the largest amount of space it can take? So right now we are talking about time because we're counting iterations and each iteration takes some time. So n by 8 after iteration 3, that's 2 to the power 3. And I think then you can start to see the trend here that after the kth iteration, you will end up with n divided by 2 to the power k elements. Now, when does the iteration stop? So the final iteration is on an array of length 1. And that is when we access that last element and check whether after all this checking, the last element is equal to the index or not. So we can do n divided by 2 to the power k. And if we set that to 1, we can rearrange the terms and we get back n equals 2 to the power k. So after the kth iteration, if you want to be left with one element, then that means n divided by 2 to the k should be equal to 1, or n should be 2 to the k, or in other words, k should be equal to log n. Remember logarithms? And here obviously log refers to log to the base 2. But what I will argue is that you can change the base of the logarithm and that will simply add a constant. So that will simply, if you're taking the natural log, then that will simply add a constant here. And remember, when we talk about time complexity, we ignore constants. So we can just generally say that our algorithm, binary search, has the time complexity of order of log n. That means as the input grows, the amount of time taken by binary search is proportional to the logarithm of the number of elements in the list passed to it. Or the amount of time taken is logarithm to the size of the initial search space. And you can verify this. You can verify that the space complex, you can check this out by simply writing it out as well. You can take some examples. Let's say you take a card list of size 10 and then work through it, the worst case, and count how many iterations you have and compare if that is close to log n or not. And then as an exercise, you can verify that the space complexity of binary search is order 1. You can try posting in the YouTube comments or in the YouTube live chat how the space complexity of binary search is order 1. But I'll let that stay. So let's now compare linear search with binary search. How are the two different? And what we'll do is we will create a large test case, because you start to see the benefits of the difference between the order n algorithm and the order log n algorithm only when you have larger test cases, because small test cases, everything runs instantly. So it's not really that much of a hassle. So here we have a locate card linear, and this is the linear version of the algorithm where we simply go through each of the cards one by one. And then we have a really large test case here. So we have the input, and then we have the cards, which goes in the range. Okay, let's see. So that's 1 to 3. So that's 1000, another 3, that's million. So we have 10 million elements here. So we have 10 million elements. And we are looking at, so we are actually creating a range here. So we are using a function in Python. So we are creating a list of numbers going down from 10 million all the way to 1. So a decreasing list going from 10 million to 1. And this is how you create it, and you can check it out. And in this list, we are looking for the number 2, which occurs at the very end. So we are sort of creating, this is, as we will see, if you want to really analyze it, this is going to be a worst case scenario, both for linear search and for binary search, approximately worst case. So the query is 2. And then the output is, this is the output that we expect, obviously, because 0 to 9999999 are the array indices, and the last element is 1. So the element just before is 2. So this is the expected output. Great. So now we have this large test. Let us call evaluate test case, and let us pass check the linear search, pass in the last test. And because this is a huge list, we may want to turn off the display of the output. We may not want to actually see the input being displayed. So we can simply turn off the display by passing display equals false. And we can just get back the result from the evaluate test case function. So the result will give the output, the actual output of the function, whether the test passed, and the running time of the algorithm. So it takes a second. So it looks like the test did pass. Our algorithm is correct. So that's great. And it took 1224.291 milliseconds, or about 1.2 seconds to answer it. And you can probably tell why, because this is the result. So it probably took 9999998 iterations. So it had to go through all the elements to get to the very end. On the other hand, when we talk about binary search, so now we are passing in the binary search version, once again turning display to false, and we are displaying the output. Okay, so this time the result is the same. The test did pass, but the execution time is 0.019 milliseconds. So that's 55,000 times faster than the linear search version. And in fact, you can tell how many elements we actually had to access. So if we just check log of, so log of this number is about 7. And maybe, if you're checking log 2, we can maybe check something like this. So not more than 20 elements had to be accessed. So where linear search needed to access about 10 million elements, binary search was able to get to the answer with just about 20 checks. So that's a lot of time saved. And you can increase the size of the array by a factor of 10 and increase this by a factor of 10 as well. And then you will see far bigger difference, where for a 10 times larger array, linear search would run for 10 times longer, whereas binary search would only require 3 additional operations. So the linear search would go from 10 million operations to 100 million operations. Binary search would go from 20 operations to 23. And that is the real difference between the complexities order n and order log n. And as the size of the arrays grows bigger, another way to look at it is that if you just divide the complexities, binary search runs n by log n times faster than linear search for some fixed constant, because there's always some constants involved. And as the size of the input grows larger, the difference only gets bigger, the difference in performance. And that is what analysis of algorithms and optimization of algorithms is all about. It's about overcoming the limitations of computers by devising clever techniques to solve problems. And it's something that you can actually apply in real life as well. In a lot of cases, there are a lot of things that you may see a brute force solution to, but if you just apply your mind, you may find a more optimal solution, a more easy way or a more lazy way to do it with less work. So think about that. And here is a graph showing how you can compare common functions, how the running times of common functions vary. So we will look at all kinds of functions. We will look at constant time functions order 1. For example, accessing an element from an array is order 1. So even if you have an element of a list of 10 million elements, you can access the last element in constant time. On the other hand, we've looked at binary search, which is order log n. And we've also looked at linear search, which is order n. Now in the future, we will look at other techniques which have complexities of n square, n cube, n to the power n, or far, far higher. And somewhere in between, there is a very nice special type of complexity called n log n, which is rather nice. So we'll talk about that as well. N log n, in fact, a lot of questions in coding assessments and coding interviews tend to be taking algorithms which would have n square complexity in a brute force approach and optimizing them either to order n or to order n log n. So we'll discuss all of this. So don't worry if this doesn't make sense just yet. But I hope you see now why we ignore constants and lower order terms while expressing the complexity of the big O notation. So we've covered binary search, but we've seen it in the context of a problem. And now we can step away one more step and abstract it out further and identify the general strategy behind binary search. And this general strategy is actually applicable to a wide variety of problems. And this is what you want to keep doing as a programmer. You need to abstract away, peel away the layers of specific problem, specific details, and find the general technique, find the general strategy, and then encode that using your functions and programs. So here's the general strategy. Come up with a condition to determine whether the answer lies before, after, or at a given position. So we are assuming here that we have some kind of a range and we have to identify a position within a range, or maybe an element within that range, but we can access elements using the position. So come up with a condition that first tells you whether given a position, the answer lies at or before or after that position. Once you have that condition, first retrieve the midpoint and the middle element of the list. Now, if the middle element or the midpoint is the answer, then return the middle position, that is the answer. You're done. If the answer lies before it, repeat the search. So repeat the process with the first half of the list or the first half of the search space. And if the answer lies after it, repeat the search with the second half of the search space. So here is the generic algorithm for binary search implemented in Python. And you can see a classic detailed documentation here. So here you have the binary search is going to take a search space low and high. So low is going to be 0 and high is going to be, well, we will pass in maybe the final position, the final index of the array. But writing it this way rather than passing an array also allows you to use binary search for problems that are not based on arrays. Sometimes these could just be numbers. For example, if I ask you to find a number between 1 million and 10 million that is a perfect square, then you can use binary search to do that. Then it takes a condition. So what it does is it starts a loop. So while low less than equals high, we get the midpoint. So low plus high divided by 2, that gives us a midpoint. Then remember earlier we had this condition test location. So our condition simply is supposed to take the middle position and identify if the middle position is the answer or we need to go left or right. So the condition should return either found, left or right. So if the condition returns found, we return the midpoint as the answer. If the condition returns left, we return the high. We move to the left side. So which is we take the end of the search space and set it to before the midpoint. So we set high equal to mid minus 1. And if the condition returns right, which is the else case here, we set low to mid plus 1. So we take the start point of the search space and move it after the element. Then we return -1. So that's your generic binary search algorithm. And if you start using this, what will happen is now this is a tested piece of code. And in fact, we can see it here. Now we can rewrite locate card, and locate card can be, we're passing in cards and we're passing in the query, and we need to write a condition. And here we're using a very interesting feature of Python. We are writing a function inside a function. So this is called function closure, and it's a very handy feature. So now we can simply write condition inside locate card. And what that does is binary search is going to pass the middle value, the middle position, but condition can also access cards and query. So which is because it lies inside locate. So what we do inside condition is, okay, we get the middle element, cards mid. If cards mid is equal to query, then here we have that check. We check whether it is the first occurrence of query or can query occur before it. If query occurs before it, we return left, else we return found. And then these are the original conditions that we already had. So you can verify this by going back and checking. But the important part here is now the while loop has gone away. Now we can simply call binary search with 0, len cards -1. So the start index, the end index, and the condition. And we can evaluate the test cases, and you can see that the test cases are correct. And now you can use this binary search function because we have now tested it with one problem. You can use this exact same function to solve other problems too. In some sense, it is a tested piece of logic. So here's what we'll do. We'll take a quick question and we will implement it. Now we've spent 1.5 hours talking about a particular problem, but let's spend maybe 2 minutes talking about a new problem and solving it. So now here's a slightly related question. Given an array of integers sorted in increasing order, find the starting and ending position of a given number. So once again, you have a sorted array. This time they're increasing. The only difference is now, apart from the fact that they are sorted in increasing order, the other difference is that we are looking for both the start index and the end index. So we're looking for both the start index and the end index of a particular number because the number can repeat, like we saw one example. And there's a very simple way to solve this. A simple strategy is do binary search once to find the first position. And that's what this function does. I'll let you read through it. The only changes here are this variable, this has changed this order because now the elements are in increasing order. And then the second change, and there's no other change here. So there's just one change here. And then there is another function called last position. Here, instead of checking the left, we are checking the right. So instead of checking mid -1, we are checking mid +1. And if mid +1 equals a target, we go to the right. And of course, we have the same change here in this code because instead of decreasing, we have increasing order, right? So now we write two functions, first position, last position. And then first and last position is simply getting the first position once. So that's one binary search, and getting the last position once. That's two binary searches. And that's not bad. Now the complexity is still order log n, 2 times log n or 2 times some constant times log n. When you express it in the big O notation is still log n. So that's okay. And that was quick. We were able to reuse most of the code that we have written. And that's the benefit of making generic functions like binary search. And in fact, we can test a solution by making a submission here. So let's go to leetcode.com. Here what I've done is I have already copied over the binary search function, the first position function, and the last position function. So by the way, LeetCode is a great platform for practicing. So you can go to leetcode.com, sign up with any account, and you will find a lot of problems, especially in the problems tab. And here you can see that this is exactly the problem that we have been solving just now. So we just post the code here, binary search, first position, last position, first and last position. And lead code requires you to write this class called solution. This is something that they give you beforehand. And inside the solution, you need to define a function called search range, where we are simply calling our first and last position. Here, I'll let you see. And we can test this code with a test case. So you can pass a test case here and test it out. Great. Or we can simply submit it. And here you can see that the problem was submitted successfully. And it tells you things like how much runtime it used, what was the memory it used, and our solution was accepted, right? So check out leadcode.com, go to the problem section, and you can see all the different problems that they have. You can also explore, and you have different problems that come up every day. It's a great place to practice. So that's binary search for you, but I just want to revisit the method once again. So this is the systematic strategy that we've applied for solving the problem. We state the problem clearly and we identify the input and the output formats. This shows that you've understood the problem, you know what the solution will look like. Then come up with some example inputs and outputs and try to cover all the edge cases. So this shows that you are envisioning what are the different inputs that can come in before you write code. Then you come up with the correct solution, not necessarily the most efficient one, and state it in plain English. Now, when you try to state it, you will have to clarify it, and that will help you clarify your own thoughts. And then you can analyze the algorithm's complexity, and you can implement the solution and test it using example inputs. So this is the basic solution. Now, in interviews and in coding assessments, maybe, where there is a time limit, you may not want to implement the brute force solution, because then you may get stuck in fixing issues with brute force and you can directly jump ahead to step 5. But while you're practicing, always implement brute force. Then step 5, analyze the algorithm's complexity. And most of the time, it is simply a matter of counting the number of iterations, how many times a while loop or maybe a loop within a loop is getting executed, and identify inefficiencies. And if it is a brute force solution, it's generally quite easy to see the inefficiency. For example, in this case, the inefficiency was that we know that the array is sorted, that anything we do will be better than going line by line, right? We could pick a random element and that would help us eliminate a good chunk of the array. So that is the inefficiency. And then apply the right technique. And we are learning the techniques. So we've learned binary search today, and then we are going to learn a lot more techniques that are asked in interviews. So apply the right technique to overcome the inefficiency and repeat steps 3 to 6, which is go back and come up with the correct solution with the optimized technique, implement the solution and test it using some example inputs, and then analyze that algorithm's complexity and identify any inefficiencies. So what we've done for you is we have created a template. So you can see this Python problem solving template. And how you can use this template is to simply run it. So you run the code, you run this template, and then when you run the template, inside it, you will see this question mark in a bunch of places. So you can give it a nice project name and you can commit it to your profile. One way you can save a copy over this template to your profile is by clicking the duplicate button. Now, if you click the duplicate button, you can copy it in your profile and you don't have to look for it. You can just find it on your Jovian profile. But anyway, once you have it copied, you can click the run button and then click run on binder and run the template. Then you go down once you run it and you can copy over a problem statement. You can copy over a link to the problem so that when you need to make a submission, you can go back and refer. And then here the method is summarized for you. And here we have created sections for you. So you can simply start filling out this method. So step 1, step 2, step 3, step 4, step 5. So whenever you're faced with a difficult problem, just use this template, and I guarantee it, if you work through this course, you will be able to solve a majority of the problems that you come across. And specifically, even if you are able to follow maybe about 30 to 40% of this course, you will easily be able to solve most questions that are asked in interviews. Because questions asked in interviews are fairly simple in terms of the data structures or algorithms they test, but the intention there is more to test your approach, look at the quality of your code and see how clearly you're expressing yourself, right? And this is exactly what this method teaches you to do. Now, to encourage you to do this, to encourage you to try it out, and you can take problems from places like LeetCode, CodeChef, Codeforces. There are a few links listed here. You can see practice problems. There are a bunch of links listed here. So that was today's lesson. For the next lesson, common data structures in Python. So this is Data Structures and Algorithms in Python, an online certification course brought to you by Jovian. Thank you. Hello and welcome to Data Structures and Algorithms in Python. This is an online certification course being offered by Jovian. Today we're looking at Assignment 1, Binary Search Practice. So let's get started. First thing we'll do is go to the course website, pythondsa.com. On the course website, you can enroll for the course and view all the previous lectures and assignments. For assignment 1, you may want to review the video and notebook for lesson 1. Let's open up assignment 1. It's called Binary Search Practice. Now in this assignment, you will apply and practice the concepts that we covered in the first lesson. So you will understand and solve a problem systematically, implement linear search and analyze it, and optimize the solution using binary search and ask questions and help others on the forum. Let's open up the starter notebook for the assignment, which contains that problem statement and other information. Now this is a notebook you're looking at hosted on Jovian. You can see some description here, and if you scroll down below, you can also see some code. And you will need to execute this notebook, modify the code within it, and record a new version which you can then submit to see your score. So let's start reading through it. As you go through the notebook, you will find 3 question marks in certain places. To complete the assignment, you have to replace the question marks with appropriate values, expressions, or statements to ensure that the notebook runs properly end to end. Now keep in mind that you need to run all the cells. Otherwise, you may get errors like name error or undefined variables. You should not be changing any variable names or deleting any cells or disturb any existing code. You can add new code cells or new statements, but do not redefine or do not change some of the existing variables. You will be using a temporary online service for code execution, and we'll see how to use it in a moment. So keep saving your work by running jovian.commit at regular intervals. And then the question marks optional will not be considered for evaluation. Although we recommend doing them, they are for your learning, but you can make a submission before you have solved the optional questions. Now you can make a submission back on the assignment notebook page, and we'll see how to do that. And if you're stuck, you can ask for help on the community forum. It's listed here. And we'll see how to do that as well. Now, one final thing I want to mention is you can get help with errors or ask for hints. You can even share your code and errors that you are getting in the code, but please don't ask or share the full working answer code on the forum. This is so that everybody has the opportunity to work through the problem statement on their own, make mistakes, learn from their own mistakes, and arrive at the right solution. Now, how do you run this code? The recommended way to run this code is by clicking the run button at the top of the page and selecting run on Binder. But you can also run it using some other options like Google Colab or Kaggle, or you can run it on your computer locally. So we're going to use the recommended method, run on Binder. Now we have the notebook running in front of us. The first thing I like to do is go to kernel and click restart and clear output so that we can see all the outputs of the notebook from scratch. And I'm also going to toggle the header and the toolbar so that we can zoom in a bit. So now the same Jupyter notebook is now running online on a platform called Binder. And before starting the assignment, let's save a snapshot of the assignment to our Jovian profile so that we can access it later and continue our work. So I'm going to run pip install Jovian. This is going to install the Jovian library. Then run import Jovian to import the library and set a project name. Here I'm just calling it binary search assignment, and run jovian.commit. Now you've taken a starter notebook which was hosted on my profile, and then you've run it on Binder. As soon as you run jovian.commit, a copy of the starter notebook gets saved to your profile. So what you will see here is a link to a notebook hosted on your Jovian profile. Let's open it up here and see. So now this is your personal copy of the assignment notebook, Any changes that you make here and run jovian.commit will get added to your profile. So if you want to come back and continue your work, then you do not have to go back to the original starter notebook, which contains all blanks. Rather, you can come back to your profile, and you can come to your profile simply by opening jovian.ai. And on your profile, you can go to the notebooks tab. And on the notebooks tab, you will be able to find, as you can see here, you will be able to find the binary search assignment here. There you go. This is the binary search assignment that we just created. And you can open it and run it on Binder to continue your work. So moving along, this is the problem we are looking at here. You are given a list of numbers obtained by rotating a sorted list an unknown number of times. Okay, so we have two new terms here, rotating a sorted list. And don't worry if you don't know what that means. Normally, if you see any new terms in a problem, they will be explained somewhere within the problem itself. For instance, here you can see that there's a definition. We define rotating a list as removing the last element of the list and adding it before the first element. For instance, rotating the list 3241 leads to removal of the last number and then placing it at the very beginning. So you end up with the list 1324. This is a new operation that we are defining. This is not something standard, but you will find that a lot of problems will define new terms or new operations so that it becomes easier for you to understand the problem. So that's rotating a list. Now rotating a list once produces 1324. Now if you rotate that list again, the resulting list one more time, then you will end up with 4132 and so on. And then the other term is sorted. So sorted refers to a list where the elements are arranged in increasing order. In this case, we have numbers, and the numbers 1, 3, 5, 7 are arranged in increasing order. So this is a sorted list. But if this was 3, 2, 4, 1, well, the numbers are not arranged in increasing order. So that's not a sorted list. So you are given a list of numbers obtained by rotating a sorted list an unknown number of times. For instance, this sorted list 0, 2, 3, 4, 5, 6, 9 is rotated a certain number of times, and you can verify that if you rotate this 3 times, you end up with the list 5, 6, 9, 0, 2, 3, 4. Right? You can see that first 9 comes to the beginning, then 6 comes to the beginning, and then 5 comes to the beginning. So you need to write a function, and you're given just this, the list. You're not given the original sorted list. You're given the list obtained by rotating some sorted list an unknown number of times. Now you need to write a function to determine the minimum number of times the original sorted list was rotated to obtain the given list. Your function should have the worst case complexity of order log n, where n is the length of the list. And you can assume that all the numbers in the list are unique. Okay, so 3 parts. Write a function to determine the minimum number of times you need to rotate the original sorted list. In this case, it is 3. The function should have the worst case complexity of log n. So this determines correctness, and this determines efficiency. And then this is some additional information to help you, that you can assume all the numbers in the list are unique. If this was not mentioned, you would also have to handle the case where your list does not contain unique numbers. Now we will apply the method that we have been applying all throughout this course for solving the problems. Number 1, state the problem clearly, identify the input and output formats. Number 2, come up with some example inputs and outputs and try to cover all the edge cases. Number 3, come up with a correct solution for the problem and state it in plain English. Number 4, implement the solution and test it using some example inputs. And having test cases and then implementing a solution allows you to test them using the example inputs and fix any bugs. That's why it's very important to have some test cases. Number 5, analyze the algorithm's complexity and identify any inefficiencies. And number 6, apply the right technique to overcome the inefficiency. And then you go back and repeat steps 3 to 6. Come up with a correct solution, implement the solution and test it, and analyze the algorithm's complexity. And you can review lesson 1 for a detailed explanation of this method. Now let's apply it step by step. The first step is to state the problem clearly and identify the input and output formats. Now, while it is stated clearly enough, it always helps to express it in your own words in the way that it makes it most clear for you. And this is something that you can keep returning to rather than the original problem statement, because this is something that you will understand better. And it's okay if your problem overlaps with the original problem statement, but do try to express it in your own words. So in this case, what I've just done is I have double clicked here. So once you double click, you can now edit this text cell, and now we can start writing a problem. So let's say given a rotated list, we need to find the number of times it was rotated. And okay, I think what I've probably missed here is that it is a sorted list. So given a sorted list that was rotated some unknown number of times, we need to find the number of times it was rotated, right? Maybe I'm just going to say given a rotated sorted list, because technically the input is not a sorted list, it's a rotated sorted list. So given a rotated sorted list that was rotated an unknown number of times, we need to find the number of times it was rotated. Now doing this exercise helps you determine if you've understood the problem correctly. And you may often find that, okay, there's a certain detail in the problem that you missed. Okay, but at this point, I'm happy with my description. And you will see that it is matching the description to a large extent. But it's something that I understand better. So I'll just refer to this from this point. Now I'm assuming here that I know what rotation and sorted means. Otherwise, I could also include those. Then here's a question. The function you will write will take one input called nums. What does it represent? And give an example. Okay. So once again, we double click on this, and one input is nums. So this is a sorted rotated list. And let's give an example here. Let's say we take the sorted list 3, 5, 6, 7, 9, and then we rotate it a few times. Let's say we rotate it a couple of times. So we end up with this sorted rotated list. So that's our input. So we've answered the question here. Now the first question was to express the problem in your own words. This is the solution. The second question was, what does the input nums represent? Give an example. It represents a sorted rotated list 7, 9, 3, 5, 6. The third question is, the function you will write will return a single output called rotations. What does that represent? Well, you have to write a function that identifies how many times the list was rotated. So this is the number of times the sorted list was rotated. Okay. And in this case, the example that we have is that this sorted list was rotated twice. 3, 5, 6, 7, 9 was rotated 2 times. So you mentioned 2 here. Now you can see these back quotes that I'm using here. This is next to the number 1 on your keyboard or below the escape key. What these back quotes let you do is they let you express text as code within Markdown. You can see that they have a gray background and they have a different font. This looks a lot more like code. Same is here true for nums. So you can use Markdown and its features to your advantage to organize your descriptions and your text better. Okay, so now based on the above, we can now create a signature of our functions. We have a function called counts rotations. It takes a list of numbers and it returns. Well, right now we're just putting pass in here, but we know that it's going to return a single number rotations. Now, after each step, remember to save your notebook. So we are going to just run jovian.commit. And now if you leave your computer, you do not have to be worried that your work may be lost. So you can go in here and you can open up this notebook from your Jovian profile and press run at any point to run this notebook. Now step 2 is to come up with some example inputs and outputs and try to cover all the edge cases. And our function should be able to handle any set of valid inputs. So here is some variations that you can encounter. A list of size 10 rotated 3 times, a list of size 8 rotated 5 times. So these are 2 generic examples. And then a list that wasn't rotated at all, a list that was rotated just once, a list that was rotated n-1 times, where n is the size of the list, a list that was rotated n times. And what do you mean by rotating the list n times? Well, let's see. An empty list and a list containing just one element. And if you can think of more test cases, you should definitely add more test cases here. And what we'll do is we will express our test cases as dictionaries. So this will help us organize the test cases and test them all at once more easily using helper functions. So you can see here that we've organized one test case here and we've expressed the test case as a dictionary. So here we have the input to the test case, that is the input key, and then we have the output to the test case. Now, because a function can take many arguments, the input itself is going to be a dictionary, and then for each argument, in this case there's just one, so we just call it nums. We have the input here, and this is the size of the output. Okay, so let's create this test case, and let us then, if you want to fetch the actual input and output out of it, so here we can fetch test input nums. That's going to give us the nums. We can use test input. The output should be test outputs. This seems to be an error. And the result is count rotations num0. Okay, so this is the actual result obtained by passing the test case into count rotations. And you can see that the result we get back is none, because right now we do not have any code. It just says pass inside. And the result and the output are not equal, because the output is the number 3, but the result is none. So that's okay. Our test case is failing right now because we have not yet implemented the function. But as soon as we implement it, we expect to see the test case passing. Now, to help you avoid all of this work, we have given you a function called evaluate test case. So from jovian.python DSA, you can just import evaluate test case and then call evaluate test case with the function you want to test and the actual test case. And you can see here it prints the input that was passed in, the expected output, the actual output that was obtained, and the test result. In this case, the test result was failed. And the execution time is also printed here if you just want to evaluate if a certain implementation is faster than another. So now your job is to create test cases for each of the scenarios listed above. So here is test 0, that is same as the original test case that we had created. Now here is test 1, a list of size 8 rotated 5 times. I will let you create this, but it will look something like this. You will open up, you'll replace the 3 question marks with, let's say, a list of size 8. So 1, 2, 3, 4, 5, 6, 7, 8. And you can imagine that if this was rotated 5 times, then 1, 2, 3, 4, 5. 5 of these numbers will then move to the first position. And you get this as the input numbers. And the output, well, it was rotated 5 times. So I think you can guess that the output here should be 5. Now here is a list that wasn't rotated at all. What should be the output here? I'm sure you can guess that the output here should be 0. So I'll let you fill this out. Here is a list that was rotated just once. So let's fill out this one. So this list rotated once would give us 7, 3, 5. There you go. A list that was rotated n-1 times, where n is the size of the list. Okay, I'll let you do that. A list that was rotated n times, where n is the size of the list. Okay, what does that look like? So you take this list and then you first put 10 in the first position, and then you put 9 in the first position. So 9, 10 comes to the beginning, and 3, 5, 7, 8 comes after it. Then you move 8 to the first position, then you move 7, then you move 5, then you move 3. If you move all of these back to the first position, you end up with the same list. So you've rotated it n times. Now, what should be the output in this case? There are about 6 numbers here. So is the output 6? I don't know, I'm not so sure, because remember the question, the original question says, write a function to determine the minimum number of times the original sorted list was rotated to obtain the given list. So it has to be the minimum number of times. So we may want to just go back and change this. We need to find not the number of times it was rotated, but the minimum number of times it was rotated, or it needs to be rotated, right? So coming back here, the output should be not 6, but 0. So keep that in mind. Then here's an empty list. I'll let you figure out what should be the nums and the output here. And here is a list containing just one element. Once again, should be pretty straightforward. Can you rotate a list with one element? I'll let you decide. And then we are taking all the tests and putting them into a single list. Now, since I have not defined all the tests, I am not going to use this definition which contains all the tests, but I'm just going to pick the number of tests that I have defined. So we have defined here test 0, test 1, test 3, test 5. I'm just going to put in test 0, test 1, test 3, and test 5. And that's the full set of tests that we have. Now you definitely need to fill out all the test cases, and if you can think of some other cases that you should be testing, then you should include those test cases here as well. Okay. Now to evaluate your function against all the test cases together, you can use the evaluate test cases helper function from Jovian. So there are two functions. Evaluate test case works with a single test case, and evaluate test cases works with a list of test cases. So we have a list of test cases here. I have 4, but you should have about 8 at least, and a few more if you've created them. So we can import from jovian.python DSA evaluate test cases, and then invoke evaluate test cases with the count rotations function. Still, we don't have any logic in the function, so all the test cases should pass, and the list of test cases we've created. So you can see test cases 0 fails, 1 fails, 2 fails, 3 fails. So out of the 4 test cases, none of them have passed. No problem. We have completed step 2, which is to create some test cases, and we'll know once we've defined a function whether the function definition is correct. Now the next step is to come up with a correct solution for the problem and state it in plain English. And there's a hint here for you already. Coming up with the correct solution is quite easy, and it's based on this simple insight. If a list of sorted numbers is rotated k times, so you keep rotating it step by step, moving the last number to the first position, then the smallest number in the list ends up at position k. Okay, and you can verify this. It's very simple to do this. Whenever you have a doubt, just create a new cell. By the way, you can create a new cell by clicking on the left side of a cell and clicking insert cell below. Or if you're in a code cell, just click here near the prompt and press the B character. And that adds a new cell below. So let's take the list 1, 3, 5, 7, 5, 6, 7. And let's rotate it k times. And let's try with k equals 2. So if you set k equal to 2, then you're going to take 2 of these numbers from the very end and move them to the beginning. So that means 0 comes at position, 6 comes at position 0, 7 comes at position 1, and the starting element in the sorted list now comes at position 2. That's interesting. Let's move the third element as well. Okay, so now we've moved 3 elements or rotated the list 3 times, and the smallest element ends up at position 3. So it seems to hold true, and you can verify this now with a larger list, smaller list, empty list, and all the test cases that you have. And if a list was sorted k times, sorted list was rotated k times, then the smallest number in the list ends up at position k, counting from 0. Further, it is the only number in the list which is smaller than the number before it. And you can see this once again. The smallest number is at position 3, and all of these numbers are higher than the numbers that come before them, except the number 1, which is smaller than 7. So we simply need to check for each number in the list whether it is smaller than the number that comes before it. If there is a number before it, then our answer is simply, which is the number of rotations, is simply the position of this number, right? So if you can find the position of the number which is smaller than the number that comes before it, the position of the number is also equal to the number of times the sorted list was rotated. And if we cannot find such a number, then the list wasn't rotated at all. And that's it. You can see here in this list, now applying this logic, 3 is the number, the smallest number. And not only that, 3 is the only number which is lower than the number that precedes it, the predecessor, which is 29. And since 3 occurs at position 4, well, actually 3 occurs at position 3. 0, 1, 2, 3. The list was rotated exactly 3 times. Now we can use the linear search algorithm as a first attempt to solve this problem. And the linear search simply involves working through this list from the left to the right. So now the task for you is to describe the linear search solution in your own words. And please write it in your own words, but here's how I'm going to write it. Let's say create a variable position with value 0. So this is the position for tracking. This is for tracking the position. Then look at the number at the given position, and not only look at it, but compare the number at the, let's say, the current position to the number before it. Now, if your starting position with the value 0, maybe we may not, there's no number before it, so we may not be able to compare it with something. We may even just start with the value 1. That's all right. If the number is smaller than its predecessor, then return position, because position is the answer. We found the number that is smaller than its predecessor. There's only one such number. Otherwise, increment position and repeat till we exhaust all the numbers. Okay, simple. Now you can add more steps if your description of the algorithm requires more steps. That's perfectly all right. But at this point, we have a very clear description of the solution. Now we're starting with the position 1, not 0, because we also want to track the previous position. Now we import Jovian here and commit our project once again, and keep saving your work after every step so that you can continue your work. So now we're talking about implementing the solution and testing it. So let's implement the solution. We said that we want to start with position 1. And when should the loop be terminated? Well, while position is less than the len of nums. I guess that's fair. And then what is the success criteria? So we have if position greater than 0 and nums of position less than nums of position minus 1. Okay, so that's the success criteria here. Now you can see that there's a condition if position greater than 0 here. So we don't really need to start position at 0. We can start position at, we don't really need to start position at 1. We can start position at 0 as well. And all that will happen is this condition will get skipped and position will get incremented. And this is a good practice, because whenever you iterate over a list, you normally just want to start with 0 just to avoid any confusion later when you're reading the code, that did you intend to write 0 here or 1, etc, etc. So just put in position equals 0 here and simply skip the check here, or simply skip this comparison if position is not valid. right? So whenever you're accessing an element from inside a list or inside a dictionary, you always want to make sure that that index or that key is valid. Okay, here we are making sure that the key position -1 is valid by checking position greater than 0. In any case, we now have the logic, and finally we are saying that if the number at position is less than the number that comes before it, then we return that. And that's just going to, if it's not, then it's going to increment the position, and it's going to check again and again and again till we run out of numbers. Now, if you've exhausted the entire list, then it follows that there were no rotations, or there were n rotations exactly. In either case, the number we return should be 0. Okay. So keep this in mind. You may have the doubt, should you be returning -1 here, or should you be returning 0 here? Well, the question does specify clearly that you are given a sorted rotated list and you have to find the number of times it was rotated. Now, obviously -1 rotations are not possible. So -1 would not be a valid return value from your function. And this is the reason we write test cases too. Now let's evaluate the test case. So let's call evaluate test case for a single test case on count rotations linear, and let's see what the test case is. This is the test case here, and this is the output. We call evaluate test case with count rotations linear and test, and that gives us a linear search result. And you can see here, this was the number, the list of numbers, this was the expected output, and this was the actual output. So great, our function seems to have passed the test case. Now we can evaluate all the test cases by calling count rotations linear on all the test cases together, and that gives us a whole list of test results. Test case 0 and 1 and 2 and 3, all of them have passed. Now if you had put in -1 here, you would see that one of the test cases would fail, which is the case where the list wasn't rotated at all or was rotated n times. Okay. So that should tell you that the answer here should be 0. So that's our linear search algorithm. And at this point, you may face issues. You may feel stuck. You may not be able to figure out how to write the code. And that's perfectly all right. That's part of learning. You may face errors. You may face exceptions. For instance, if you did not have this check here, position greater than 0, or maybe what you had here was some other condition, like position less than equals position +1, and that's okay. Then you can go to the forum and post your issue. So let's open up the forum here. This is the forum discussion for assignment 1, and you can go into the original topic here, which is a longer discussion. So this is where everybody's posting small issues. So you can see that there's about 321 messages that have been posted. You can start looking through this forum. You can start reading through some of the posts. You can even search. If you press Ctrl F, and you can even search for questions here. Now, if you want to post your own question, scroll down to the very end, or you can just click this button here and click reply. Okay, and mention your question here. I have an issue. Should I return -1 or 0 in the case the list has not been rotated? Okay, maybe that's, and if you want, if you have code that's not working or there's an error, you can also include a screenshot of your code, or I'll show you another trick. You can actually include, let's say you commit your notebook. So let me come up here. I've committed my notebook. And if you have a particular line of code that you want to share, you can actually click copy cell link and paste it here. So that will give a link to the entire cell. And if somebody clicks on the link, then they can view that specific cell of the notebook directly. Let's see. You can see here that it brings us directly to this specific cell. There's another option. You can even click on embed cell. Okay, for secret notebooks, we do not allow embedding, but copying the cell link should work. And then click reply, and your question will be posted and somebody will reply to your question. Just come back to the forum in a few hours or maybe the next day and you should see an answer. You will also receive an email. So that's the discussion topic. You can also go back to the topic here, the category here, and create a new question. You can see that if you want to start your own thread, if you think your question deserves a deeper discussion where multiple people can reply, you can also create a new thread by clicking new topic. Okay, so keep this in mind and do make use of the forum. What we've seen is people who are active on the forum are at least 4 to 5 times more likely to complete the course and earn the certificate of accomplishment and continue working on these topics after the course as well. Okay, so the next step is to analyze the algorithm's complexity. And the way to do this, if you've seen lesson 1, is to simply count the number of iterations, the number of executions of the while loop. Now, if you have a list of numbers of size n, then you can see here that this is the key loop here, while position less than the length of numbers. So then there will be n loops or n iterations, and then inside each iteration we're performing certain comparisons and returning things. So all of these are in effect constant time, and based on this you can probably tell that the complexity of linear search is order of n. So you can just put in a big O n. In the big O notation, this would be order n. So that's the first part of the assignment, linear search. Now the next step is to apply the right technique to overcome the inefficiency, and that's where you can now read through the rest of the assignment. Now the idea here is this: binary search is the technique we'll apply, and the key question we need to answer in binary search is, given the middle element, can you decide if it is the answer, which means if it is, let's say, the smallest number in the list, or whether the answer lies to the left or the right of it. Okay, so if the middle element is smaller than its predecessor, then it is the answer. We already know that because there's only one number in the list that is smaller than its predecessor. So you can see here, for example, now if the middle element was 1, which it's not, but suppose the middle element was 1, and you can see that 1 is smaller than 8, then we know that 1 is the answer. So the position of the middle element is the answer. However, if it isn't, then we need a way to determine whether the answer lies to the left of the middle element or to the right of it. And consider these examples. So here you can see that the middle element is 3, and the answer is the position 2. So in this case, the answer or the smallest element lies to the left. On the other hand, in this case, you can see the middle element is 4, and the smallest element -1 lies to the right of it. So now you need to apply your mind and think of a check that will help you determine if the middle element, given the middle element, if the answer lies to the left or the right of it, right? And we're looking for the smallest element, remember. So the logic here, if you just spend a couple of minutes, you will come up with this quite easily. If the middle element of the list is smaller than the last element of the list, okay, or the last element of the range that we're currently looking at, that means that all the numbers here are in increasing order. So then the answer lies to the left of it. On the other hand, if the middle element of the list is larger than the last element of the range, that means that because we know that the list is a rotated sorted list, so that means that the numbers increase up to a point and then there's a decrease and then they continue increasing. That's the only way in which the final element can be smaller. So that means the answer lies to the right of it. So that's the logic here for binary search. And now what you have to do is describe the binary search solution in your own words. So here once again you have these 4 or 5 lines. And it's very important that you do this, because if you cannot express it, then coding it is also going to be difficult for you. So always do this exercise of expressing the solution in your own words when you're practicing, when you're solving a coding challenge or something. Even in an interview, it's also very important, because the first thing you need to do is to communicate to the interviewer your thought process and how you're thinking about the problem. So the first thing you need to do is describe a simple solution in simple words, and then they may or may not ask you to code that solution. And then the next thing is to identify the complexity or identify the inefficiency. Then the next step for you is to describe the optimal solution or the binary search solution in your own words. Okay. Now, if you don't describe the solution in your own words and you start writing the code, they may not be able to follow your code. So even if you've written mostly correct code, maybe with one or two edge cases wrong, they may still have a feeling that you don't know what you're writing. But if you explain the solution clearly to them, they will know that now you understand the solution, and they will be able to follow the code as you write it, and they will be able to pick up mistakes or errors and help you with the errors. One secret is that interviews are always open to helping you unless you make them really confused. So keep that in mind and describe the solution in your words. Once you do that, you can commit. Now the next step is to implement the solution. Now you implement the binary search solution as described in the previous step. Let's run this again. Yeah. So you run count rotations, define the function count rotations binary. Now you may want to review lesson 1 here on how to start it out. You see that low starts out at 0 and high starts out at len nums minus 1, and I will not solve the rest of this, but there is a certain condition here between low and high. So in binary search, we are starting with the entire list as the range. Then we are looking at the mid number. So we're getting the mid position, and we look at the number at the mid position. Then we check if the middle position is the answer. So if the middle position is the answer, we return the middle position. Then we check if the answer lies in the left half. So here's a condition where you decide if the answer lies in the left half, and if the condition holds true, all we do is we change the high, so we change the end point of the range to mid minus 1, and then we check if the answer lies in the right half. In that case, we change the starting point of the range to mid plus 1, and the while loop repeats. Okay, so that's the general logic of binary search. And one thing you have to keep in mind is if none of the elements satisfy the criteria that you have, what is the answer? And this is a very important condition. This is where it is very easy to go wrong. This is also called the edge case or the trivial case. So you should handle and think about this carefully. Okay. And then once you've done that, you can evaluate the test case, and you can a single test case. You can evaluate multiple test cases. Now, if your test cases are failing, you may want to enable this print statement inside by uncommenting it, but make sure to comment it out at the end once again. And the print statement will help you see what the low, high, and mid points were. Now you may want to then take up pen and paper, look at an example that is failing, and see if the printed numbers match what you expect to see. Debugging your function is a very important skill, so keep that in mind. And use a debugging technique like this by adding print statements and working out the same problem side by side on paper to fix your issues. Otherwise, you may feel lost if you're not able to look into the internal workings of the function. Next, you have to analyze the algorithm's complexity and identify inefficiencies. This should be straightforward enough. We've already looked at the complexity of binary search, but all you need to do is make sure that what you're doing within the algorithm matches the analysis that we've done earlier. So the problem size reduces by half each time, and then we are doing constant work in each step before solving a problem of half the size. So that should roughly give you an answer. And keep committing your work. Now finally, to make a submission, you have two options. Now one option is to take this link. So your notebook has been committed here, and you can come to the assignment page. Let's open up the assignment page, binary search practice. Come down here and paste this link here and click submit. Now once you click submit, the assignment will be submitted and it will go into automated evaluation. So in about a couple of minutes, maybe up to an hour, depending on the queue of submissions from different participants, you will receive a grade over email. Let's just refresh the page. And it seems like there was an issue here. The issue was that count rotations binary was not defined. So it's possible that this happened. Count rotations binary did not get defined because there are a bunch of question marks here. So we may need to then fix the issue and then come back and make a submission once again. Okay. So here I have received fail grade. I will go back and I will fix the issue and then come back. Okay. Now it's very important for you. That's why to have good set of test cases for you to test your function. So that when you submit it or when you get an error, you can maybe look at your function's performance on the test cases and fix anything that needs to be fixed and add new test cases if you need to. Now, one other way you can submit is by simply running the code by jovian.submit assignment equals python dsa -assignment1. The code is mentioned here. You can see here that the submission was made and you can verify your submission on this page. Okay, so that's assignment 1. So what should you do next? Review the lecture video if you need to and execute the Jupyter notebook. You may want to keep the Jupyter notebook running side by side as you're working on the assignment. Then complete the assignment and even attempt the optional questions. If you scroll down here on the assignment notebook, you will find that there are some optional questions for you. Here's one bonus question. Use the generic binary search algorithm. So inside the Python DSA module in Jovian, there is a function called binary search. You can use the generic binary search example. Then here's an optional bonus question 2. Handle repeating numbers. We did say that you can assume that there are no repeating numbers in the list, but here's one list with repeating numbers. Can you modify your solution to handle this special case? And then here's an optional bonus question 3 about searching in a rotated list. So you're given a rotated list. Now, instead of finding the number of times it was rotated, you're trying to find the position of a certain number, for instance, the position of 6. Can you apply binary search and modify your previous solution slightly to search within the rotated list and find the position of a given number? Okay. Now, here's a hint. You can simply identify 2 sorted subarrays within the given array and perform a binary search on each subarray. To identify the 2 sorted subarrays, you can use the count rotations binary function. So that's one potential solution. Another way is to modify the count rotations binary function to solve the problem directly. So it's a very interesting problem to solve. And if you found the assignment easy, then you should definitely solve these bonus questions. And if you can solve this question by yourself without taking additional help, then you can solve pretty much any problem related to binary search that may be asked in an interview, because most of the questions are some variations of something like this, and this is pretty much the hardest problem you may get asked. You can also test your solution by making a submission on LeetCode, and this is only for the final optional question. And there's a thread on the forum where you can discuss the bonus questions separately as well. So do make use of the forum thread too. Here it is, optional bonus questions discussion. So that was assignment 1 of data structures and algorithms. This is called binary search practice. Hello and welcome to Data Structures and Algorithms in Python. This is an online certification course by Jovian. My name is Akash and I am the CEO and co-founder of Jovian. You can earn a certificate of accomplishment for this course by completing 4 weekly assignments and doing a course project. Today we are on lesson 2 of 6. Now if you open up pythondsa.com, you'll end up on this course website where you will be able to find all the information for the course. You can view the previous lessons, which is lesson 1, and you can also work on the previous assignment, which is assignment 1. And you can also check out the course community forum where you can get help and have discussions. So let's open up lesson 2. This is the lesson page. Here you will be able to see the video for this lesson. You can watch live or you can watch a recording here. And you can also see a version of this video lecture in Hindi. And in this lesson, we'll explore the use cases of binary search trees and develop a step-by-step implementation from scratch, solving many common interview questions along the way. So here is the code that we are going to use in this lesson. All the different notebooks containing the code are listed here. And let's open up the first one. So here you can see all the explanations and the code for this lesson. This is binary search trees, traversals, and balancing in Python. And this is the second notebook in the course. You can check out the first notebook in lesson 1. And if you're just joining us, this is a beginner-friendly course and you do not need a lot of background in programming. With a little bit of understanding of Python and a little bit of high school mathematics, you should be able to follow along just fine. If you do not know these, then you can follow these tutorials to learn the prerequisites in just about an hour or 2. Now, the best way to learn the material that we're covering in this course is to actually run the code and experiment with it yourself. So to run the code, and you can see here, if we scroll down, you can see that there is some code here on this page as well. Now to run the code, you have two options. You can either run it using an online programming platform, or you can run it on your computer locally. So to run this code, we will scroll up and click on the run button and then click run on Binder. And this is going to start executing the code that we were just looking at. So once again, you can go on the course page, pythondsa.com, open up lesson 2, and you can watch the video there. And on lesson 2, you can open up the link to the code where you can read the code and the explanations here. And if you want to run the code, just click the run button and that will execute the code for you. So once you click the run button on Binder, you should be able to see an interface like this. This is the Jupyter Notebook interface. The same explanations that we were seeing on the lesson page, you can see here, the same explanations are now available here. But the difference is you can now edit these explanations and you can go down and you can actually run some of the code in this tutorial. You can see here that you have a run button, and when you click the run button, that is going to run the code in this particular cell. And this is a Jupyter Notebook made up of cells. Now we'll do a couple of things here. The first thing we'll do is we'll click on kernel and click on restart and clear output. What this will do is this will clear all the outputs of the code cells so that we can execute them ourselves. And then I'm just going to zoom in here and hide the interface so that we can look at the explanations and the code. So finally, we have some running code. And in this notebook, we will focus on solving this specific problem. And this is a common question. A question of this sort can be asked in interviews. So this is an interview question, but along the way, we will also learn how to build binary trees and binary search trees and how to apply them to several other questions. So here's the question. As a senior backend engineer at Jovian, you are tasked with developing a fast in-memory data structure to manage profile information, which is username, name, and email for 100 million users. It should allow the following operations to be performed efficiently. You should be able to insert the profile information for a new user, find the profile information for a user given their username, and then update the profile information of a user once again given their username, and list all the users of the platform sorted by username. And you can assume here that usernames are unique. So this is a very realistic problem that you might face if you're working at a company where you have a lot of users. So let's see how we solve this problem. Now here's a systematic strategy that we'll apply for solving problems, not just here, but throughout this course. The first step is to state the problem clearly and in abstract terms, and then identify the input and output formats. Then come up with some example inputs and outputs to test any future implementations and try to cover all the edge cases. And then come up with a simple correct solution for the problem. It doesn't have to be efficient, it just has to be correct, and state it in plain English. And then implement the solution and test it using some example inputs. Fix bugs if you face any. And finally, analyze the algorithm's complexity and identify inefficiencies if any. Now, once you identify inefficiencies, then we apply the right technique, and that's where data structures and algorithms comes into picture. So we apply the right technique to overcome the inefficiency, and then we go back to step 3. So come up with a new correct solution, which is also efficient, state it in plain English, implement it, and then analyze the complexity. Now, if you follow this process, you should be able to solve any programming problem or interview question. So step 1, we state the problem clearly and we identify the input and output formats. Now we can reduce the problem to a very simple single line statement. We need to create a data structure which can efficiently store 100 million records. And we should be able to perform insertion, search, update, and list operations, all of them as efficient as possible. Now the input, the key input to our data structure, the solution that we are building is going to be user profiles, which contains username, name, and email of a user. Now, before we come up with a solution, we need a way to represent user profiles, and a Python class would be a great way to represent the information for a user. So you may have heard of the term object-oriented programming, and that is what we're going to look at now. If you're not familiar with a class, it's very simple. A class is simply a blueprint for creating objects. And what's an object? Well, everything in Python is an object, whether you're looking at a number, a dictionary, a list, anything. And you can create your own custom objects with custom properties and custom methods by creating your own custom classes. So here's the simplest possible class in Python with nothing inside it. We are creating a class user. So this is how you declare a class. And then we're putting nothing inside it. So whenever you put nothing inside a function or a class or anything, you need to put the pass statement, because Python cannot accept empty blocks of code. So here we're creating a class which does not have anything inside it. And we can create an object, or it's often called instantiation, which is creating an instance of a class, instantiate an object of the class by calling it like a function. So we say user1 is user. So this creates an object and the variable user1 points to that object. Now we can verify that the object is of the class user by simply printing it or by checking its type. User1 and type user1 are both user. Now the object user1 does not contain any useful information. So let's add what's called a constructor method. So constructor method is used to construct an object to store some attributes and properties. So now we're defining the class user once again, but inside it, we're defining this function, and you can see that this function is inside the class because there is some indentation here. So we define this function underscore init, and it takes 4 arguments. Now the first argument is a special argument called self, and we'll talk about this. And then we have 3 arguments, username, name, and email. And inside init, what we're doing is we're setting self.username. So we're setting a property on self to username. We're setting a property on self to name, and we're setting a property on self to email. And finally, we're printing user created. So let's see, let's create another user, user2. And you can see that user2 is also an object of the class user. Now here's what's happening conceptually when we do this. The first thing that happens is when you invoke this function, when you invoke user as a function, Python first creates an empty object of the class user and then stores it in the variable user2. And then Python invokes the init function, and to the init function, it passes user2, the object that was just created as self, and then the other arguments that were passed while creating the object as the rest of the arguments. So you can imagine that we are basically calling user.__init, the function, with user2, an empty object, and these arguments, John, Johndoe, and johndoe.com. And then inside the init function, we simply set these properties on user2. So now we get user2.username is John, user2.name is Johndoe, and user2.email is johndoe, john@doe.com. So that's basically how classes work in Python. And that's why you always have this additional extra argument in all class methods, which will refer to the object that finally gets created. Okay, so once user2 is created with the values John, John Doe and johndoe.com, you can check that user2.name is John Doe and user2.email is john@doe.com and user2.username is John. Now you can also define some custom methods inside a class. So obviously we had the init method, but here we are also defining another method called introduce yourself. Now introduce yourself takes again 2 arguments. The first argument is self, which will refer to the actual object that gets created later. And then we have a guest name and we basically say, hi guest name, I am such and such, contact me at such and such. So these blanks are filled in using the guest name, self.name and self.email. Okay, so that's how you define a method in a class. So here we have another user we're creating, Jane and Jane Doe at jane@doe.com. And you can see here that when we call introduce yourself with David, so user3, which is Jane, becomes self, and then David becomes guest name. And that's why we get, hi David, I am Jane Doe, contact me at jane@doe.com. So that's a quick refresher on classes in Python. Now there's a lot more to classes, but the simplest thing you need to know is how to define a class, how to create a constructor, which is __ init, how to set some properties, like we said, the properties name, email, and username. And finally, how to define methods, like we defined the method, introduce yourself. And that's all we will need today. So we won't need much more than that. And one final thing that we're doing with our class is we're defining 2 other special functions, __ repr, repr, and __ str. So now these two functions are used to create a string representation of the object. And you can see here, once we create an object user4, now, and if we try to print user4, you can see that user4 is now printed like this. So user3 was not printed. I mean, user3 was printed just as a user, but with user4, we have all this information printed here as well. So now here's an exercise for you, which also brings us to the first quiz of the day. Now we are going to do 3 quizzes in this video, and you can answer these quizzes on LinkedIn. So go to our LinkedIn profile. If you see the posts, you will see a new post here, which will give you a question. And the question is, what is the purpose of defining the functions str and repr within a class? And how are these 2 functions different? Now leave a comment with your answer and we will pick the right answer, 1 right answer, and 1 lucky winner will get a swag pack from us. So that was the input. We now have a way to represent users by creating classes. And then the output that we want, the final output that we want to create for our problem is a data structure. So a data structure is once again something that we can define using a class. So we can expect our final output to be a class called user database, which has 4 methods: insert, find, update, and list all. And insert takes a user and inserts it into the database. Find takes a username and returns the user. Update takes a user and updates the data for that user. And finally, list all returns a list of the users. So this is what the class will look like, and we have not implemented it yet, but we now have an interface. So now the next step is to come up with some example inputs and outputs. So let's create some sample user profiles that we can use to test our functions once we implement them. So we're going to create these 7 user profiles, and you can see that we're creating these 7 user profiles with a username, name, and an email, and storing them in these variables using the user class that we have just defined earlier. And we're also going to store the list of users in this variable called users. And as you can see, we can access different fields within a user profile using the dot notation. So you can check biraj.username is Biraj, and biraj.email is biraj@example.com, and biraj.name is Biraj Das. Now you can also view a string representation of the user as we have seen. So if we print the user, you can see some information about the user. And here is the full list of users that we have created. So it's always a good idea to set up some input data, set up some test inputs that you can use to test with your implementation later on. And since we haven't implemented our data structure yet, it's not possible to list any sample outputs, but you can try to come up with some different scenarios to test any future implementations. So let's list some scenarios for testing the methods of our user database class. So the methods are insert, find, update, and list all. And for inserting, you may want to test that you're inserting a user into an empty database of users. So that's what's called an edge case. And then the general case is to insert a user into the database, assuming that the user already does not exist. Then another edge case is trying to insert a user with a username that already exists, right? So these are all the different ways in which we can use the insert function, and there can be some more. So here's an exercise for you. Try coming up with all the different scenarios in which you would like to test the different functions: insert, find, update, and list. So that completes step 2. Now we have some sample inputs, and then we have some scenarios in which we are going to finally test our function. So the next step is to come up with a simple correct solution and then state it in plain English. Now here's a simple and easy solution to the problem. We simply store the user objects in a list sorted by usernames. That's simple enough. And suppose we do that. So inside our data structure, we have a list which simply contains a bunch of user objects. Then the various functions can be implemented like this. So you have the insert function. The insert function simply requires looping through the list and then adding the new user at a position that keeps the list sorted. So for instance, if you have the users Akash, Hemant, and Siddhant already, and then you're inserting the user Biraj, then you can tell that Biraj should go between Akash and Hemant in alphabetical order. So that's how you insert a new user and maintain the sorted property of the list. Then to find a user, we simply loop through the list and then find the user object with the username matching the query. So that's if you're looking for Hemant, for instance, you start from the beginning, you go through Akash, Biraj, and finally hit Hemant, and then you can retrieve the user object associated with Hemant. And then you have update. Now updating is very simple as well. It's similar to find. So you find the user object matching the query and then update the details of that user object. And then finally, because our internal representation is already a list of user objects sorted by usernames, so we can simply return that list when we want to list the users. So that's our plain English description, and it's always a good idea to describe your solution in plain English so that you can clarify any doubts you have. And even during interviews, it's a good idea to have a conversation with the interviewer before you actually implement the solution. And now one fact that we can use is that usernames, which are strings, can be compared using the less than, greater than, or equal to operators. So we can compare strings just like numbers in Python. So that will make it easy for us to implement these functions. And that brings us to the implementation. And the code for implementing these is also fairly straightforward. So now we have the user database class. We are actually implementing this class. And here you see that we have a constructor, and the constructor does not take any additional arguments apart from self. And all we do is inside self, we set a property .users, and that property .users is set to an empty list. Then we come to insertion. So now assume that we already have some users in our user database. So we start out with a pointer set to 0, and we go through all the valid positions in the users list. So which is from 0 to n-1 if there are n users. And then we find the first username greater than the new user's username. So for instance, if you're inserting Hemant, then you go through Akash and Biraj, and then finally you realize that the next value is probably Siddhant. So you want to insert Hemant before Siddhant, right? So you want the first username that's greater than the new user's username. And you check this property, and as soon as you find the next user is greater than the user that needs to be inserted, we break out and then we insert that user at that position. Okay, so this is the insertion. You can, it's just 4 or 5 lines of code. So you can work through this code, try to read this code line by line and see how it works. Now, similarly, you have the find function, the update function, and the list function. They're all pretty straightforward. There's really not much here. So this is an exercise for you, because this is also the brute force or the simple implementation. So this is an exercise for you to go through each of these functions and try it out, and use the interactive nature of Jupyter to experiment and add print statements inside each of the functions if you need, inside each of the loops, if you need more visibility into what's happening. Okay. But what we will do is we will try and test this implementation out. And the first thing we do is instantiating a new database of users using the user database class. So here we say user database, and that gives us a database of users. And now let's insert some entries into this database. So we can now insert, for instance, we can insert the value Hemant, Akash, and Siddhant. So here we have inserted 3 values into the database, and now we can retrieve the data for a given user, given their username, using the find method. So now if we say database.find Siddhant, that returns a user, and we can check the value of user. And you can see that now we have retrieved the data for Siddhant, which is username Siddhant, name Siddhant Sinha, and email siddhant@example.com. Now let's try changing the information for a user. So to change the information, we can call database.update and then simply pass in a new user object. So let's say we want to change the information from Siddhant Sinha to Siddhant U. So this is how we do it. We call database.update. And now if we find the information once again, now if you call database.find once again, we get back a user object, and this time with the updated information. So we have created the database, we have inserted some values into it, and then we have retrieved values out of it, and we've also updated them. And finally, we can retrieve a list of the users in alphabetical order. So now if we list it out, you can see here that we have the username Akash, we have the username Hemant, and we have Siddhant. These are the 3 values that were inserted, and they are all in alphabetical order of username. Now if we insert a new user, let's say we insert Biraj, we can make sure that Biraj is inserted into the right position. Okay, so that's how we use the data structure that we just created. And you can use the empty cells here to try out the various scenarios when you run the notebook. So just to recap, we created a simple class inside which we are storing a list of users in sorted order of usernames. And then insertion is pretty easy. We simply loop through, find the right position, and insert any new values. Finding values is very easy as well. We simply loop through and keep comparing. And updating values is simply a matter of finding them and then updating that specific value. And listing is simple because we can simply return the internal list representation that we're already storing in the sorted order of usernames. So that's the simplest solution, or one of the simplest solutions. There can be even simpler solutions maybe. So the next step now is to analyze the algorithm's complexity and identify any inefficiencies. So typically in an interview setting, you may not want to implement the simplest solution. So you can actually skip step 4. When you've described what the simplest solution is in English, in plain English, which was step 3, you can directly jump to analyzing its complexity and then move on to optimization and implementing the optimized version. But when you are practicing or when you're learning, it's always a good idea to implement even the brute force solutions. So let's analyze the complexity. The operations insert, find, update involve iterating over a list of users, and in the worst case, they may take up to n iterations to return a result, where n is the total number of users. Now the list all function is slightly different because it simply returns an existing list. So the list all function does not take linear time, it takes constant time. Now based on this information, it's very easy to guess the time complexities of the various operations. Insert, find, and update have a order n worst case time complexity, which means they can take up to n iterations. However, the list function has an order 1 complexity, which means irrespective of how many users you have in your database, it returns the list in the same amount of time. Now, if you want to display the list or if you want to iterate over the list, that may take you additional effort, but getting the list itself is a constant time operation. So that was the time complexity, and an exercise for you is to verify that the space complexity of each operation is order 1. And if you're wondering what we mean by complexity, then you can go back and watch lesson 1 where we talk about analysis of algorithms, complexities, and the big O notation, what we're calling order of n, the big O notation. All of these explained in a lot more detail. So you can go back to lesson 1 and check it out. Now we've created a simple solution, and our first question might be to wonder if this is good enough. And to get a sense of how long each function might take if there are 100 million users on the platform, let's create a while loop. Let's create a for loop and let's run it for, let's see how many this is, 1, 2, 3, 4, 5, 6, 7, 8. So let's run it for 10 million or 100 million numbers. So here we are creating a range of 100 million numbers, and we're running a for loop which iterates over the entire range. And we're simply performing a simple operation, which we're not really using. We're just multiplying the number by itself to simulate what might happen if we have our database of 100 million users and we're trying to find a user. Now, what is the worst case scenario here? And let's run this. And you can already see that it is taking a while. For 100 million users, the loop takes about 10 seconds to complete. Here it took about 9.45. And a 10-second delay for fetching user profiles will definitely lead to a suboptimal user experience, and that may cause users to stop using the platform altogether. Now, imagine you came to Jovian.ai and it took 10 or 15 seconds to load your profile, and then maybe even longer to load the other information and display it. You would not be happy with the experience. And then a 10-second processing time for each user, for each request, each profile request will also significantly limit the number of users that can access the platform at a time. Because if you're running the backend server on one computer which has 8 cores, then each core will be busy for 10 seconds each time a user tries to access the platform. So you can only serve about 8 users in 10 seconds time. Now that's pretty bad. That could significantly limit the number of users. You will have a significant outage if a lot of users come to the platform. Or on the other hand, you may have to increase the cloud infrastructure, add more servers, add bigger hardware, more cores, more RAM. And that could increase the cloud infrastructure costs for your company by millions of dollars. So as a senior backend engineer, you must come up with a more efficient data structure. And this is why choosing the right data structure for the requirements at hand is a very important skill. Now, we can clearly see that using a sorted list of users may not be the best data structure to organize the profile information. So let's see what better we can do here. And before we do that, let's save our work. So remember that this notebook, we were running it on an online platform called Binder, and Binder can shut down at any moment because it is a free service. So what you want to do is run pip install Jovian and then import the Jovian library, and you can then run jovian.commit. Now when you run jovian.commit, what this does is this captures a snapshot of your Jupyter notebook, whether you're running it on Binder or you're running it on your own local computer, and it saves the snapshot of this Jupyter notebook on your Jovian profile. So here you can see now on my Jovian profile, I have this notebook, and I can go back on my profile and view the other notebooks that I've created in the past. So your Jovian profile becomes a collection of all the Jupyter notebooks that you're working on. So always it takes just a couple of lines, import Jovian and run jovian.commit. So always run jovian.commit inside your notebooks. And if you want to resume any work that you were doing, then all you need to do is click on the run button and then click run on binder once again. And then you can start executing the code within the Jupyter notebook once again, right? So remember that binder is a free service, so it will shut down if after about 10 minutes of inactivity, which is if your computer goes to sleep or you change your tab. So keep running jovian.commit from time to time. So now we have a simple implementation and we've analyzed it and determined that it is not efficient, it is inefficient. So now we need to apply the right technique to overcome the inefficiency. And we can limit the number of iterations required for common operations like find, insert, and update by ditching the linear structure that we had earlier and organizing our data in a more tree-like structure. So this is a structure that we'll use for our data, and we will call this a binary tree. Now this is called a tree because it vaguely resembles an inverted tree trunk with branches. So you can think of this as the root. So this as the root, and then you can see each of these are like branches. And then there are nodes where branches then split into multiple branches. So these are called nodes. And finally, at the end, you will have individual nodes which do not have any more branches, and those are called leaves. So these are some terms that are used. The tree represents the entire structure. The top node is called the root, and each element in the tree is called a node. The top node is called a root. And then the bottommost nodes, which do not have any sub trees or what are called children, which do not have any children, are called leaves, right? So the root node has 2 children, and then each node therewith can have 0, 1, or 2 children. So it's not necessary to have exactly 2 children, but up to 2 children is what determines a binary tree. So that's a binary tree. But the binary tree that we need will have some additional properties, which is what will make it efficient for our purposes. So you can see one thing you can observe here is that the root node also seems to be the central value if you sort the keys in increasing order. So what you will notice is on the left, we have keys which lie before Jadesh, and on the right, we have keys which lie after Jadesh. So that's one thing. And that is actually the second property listed here, that the left subtree of any node consists only of nodes which have keys that are lexicographically smaller than the node's key, right? So the key for this node is Biraj, and that is lexicographically smaller than Jadesh. And similarly, Hemant and Akash are all smaller than Jadesh. And then this property holds at every node. So at every node, if you check Sonaksh, you can see that Siddhant is less than Sonaksh, and Vishal, which comes to the right, is more than Sonaksh. And then Sonaksh, Siddhant, and Vishal, all three are greater than Jadesh, right? So when a binary tree satisfies this property, it is called a binary search tree. So that's what we're looking at here. This is a binary search tree. So that's the first property that we need. The second property is that our nodes will have both keys and values. Now, sometimes you can create binary trees with just keys. Each node will have a single number or a string inside it, and you can call it the key or value or element or whatever you wish. But what we want is the keys to be usernames so that we can compare the keys easily. But along with each node, we also want to associate a value, which is the actual user object. So if we're looking for Hemant, let's say we start at the root node, we see that Jadesh is the root node. And since it is a binary search tree, we know that Hemant lies to the left. Then we reach Biraj. We know that Hemant will lie to the right of Biraj. So we go right, we reach Hemant. And then we access the value stored at Hemant, which is the user details for Hemant, right? So we need both keys and values in a binary tree. And this is what is called a tree map or a map in many languages. And then finally, this tree that we will create, this data structure that we will create, it will be balanced. So here what we're looking at is each node has 2 children left and right, but it is also possible to have an unbalanced tree where you only have one child on each on maybe one of the sides. So we will require it to be balanced, which means that it does not skew too heavily in one direction. And we'll talk about what balancing means, and we'll talk about how to check if a tree is balanced and how to keep a tree balanced. Okay. So we'll go over all of these things step by step, but these are some of the properties that we want our final data structure to have. Okay. So one important property of a tree, of a binary tree, is the height of a tree. In fact, if you start counting, you can say this is level 0, where you have one node, and this is level 2, or this is level 1, where you have two nodes, the left and right child of the root node. And then this is level 2, where you have four nodes, the left and right child of the first node on level 1, and the left and right child of the second node on level 1, right? So you can see that the number of nodes in each level in a balanced binary tree is double of the number of nodes of the previous level. So if you have a tree of height k, or which means a tree which has exactly k levels, then here's the list of the number of nodes at each level. Now level 0 will have one node, the root node. Level 1 will have two nodes, its children. Level 2 will have four nodes, their children. So that's 4 nodes is 2 times 2, or 2 to the power 2. Level 3 will have 8 nodes, 2 nodes for each of these 4 nodes. So that's 2 to the power 3. And similarly, if you keep going down, level k minus 1, the final level, will have 2 to the power of k minus 1 nodes. So that if the total number of nodes in the tree is n, then it follows that n is 1 plus 2 plus 2 square plus 2 cube plus so on plus 2 to k minus 1. Okay. So what we're trying to determine here is what is the relationship between the height of the tree and the total number of nodes in the tree. And this is the relationship, and we can simplify it a bit. If we add 1 to each side, you can see here that this side we get n plus 1, and this side we get 1 plus 1, which gets simplified as 2, or 2 to the power 1. And then we can add 2 to the power 1 with 2 to the power 1, and that gets simplified as 2 to the power of 2. Then we can add 2 to the power of 2 and 2 to the power of 2, and that gets simplified to 2 to the power of 3. And we can keep performing this reduction. We can keep adding these together till we finally end with 2 to the power k minus 1 plus 2 to the power k minus 1, which is simply 2 to the power of k. So what that gives us is that k, the height of the tree, is log of n plus 1, which is approximately, or in almost in every case, less than log n plus 1. So that's a bit of an approximation we're doing here, but it is the height of the tree is less than log n plus 1. So to store n records, we require a balanced binary search tree of height no larger than log n plus 1. Now this is a very useful property in combination with the fact that nodes are arranged in a way that it makes it easy to find a specific key simply by following a path down from the root, the binary search tree property. And we'll see soon by the end of this lesson that the insert, find and update operations in a balanced binary search tree have complexity order of log n. So in our original implementation, our brute force implementation, they had order n, and this time we've reduced the complexity to order log n, and that is far better. And we'll see how that happens. Okay. So that's a quick introduction to binary search trees. We've had enough theory now. Let's get into some implementation. But before that, we have the second question. Now, binary trees are very commonly used as data structures for a variety of different languages. For instance, Java, C++, Python. Java and C++ have this concept of a map, which is represented using a binary tree. And it is also used in file systems. So binary trees are also used in file systems to store indexes of files. So when you browse your file system or when you search for a specific file, it is a binary tree that is used to look up the file and find the location of the file. Now that brings us to our second question of today. Now you can find the second question on our LinkedIn profile. So once again, go to linkedin.com/school/jovianai. And you will find the second question here. The second question is, which tree-based data structure is used to store the index in the Windows file system, and who invented this data structure? So like this question, follow us and comment with your answer. And you can stand a chance to win a swag pack, right? So if we repeat the question, which tree-based data structure is used to store the index in the Windows file system, also known as NTFS, and who invented this data structure? Okay, so let's get to the implementation of binary trees. And here's a very common interview question that you might get. Implement a binary tree using Python and then show its usage with some examples. So what we'll do as we implement binary trees and binary search trees is to also cover many common interview questions. In fact, we'll cover exactly 15. So that's quite a few. And the first one is to implement a binary tree. And to begin, we'll create a very simple binary tree. So we will not have any of the special properties like key value pairs and binary search tree and balancing. Rather, and we'll also use numbers as keys within our nodes because they're simpler to work with. So here is an example binary tree. So we have a root node and then we have a left child and a right child. And here's a simple class representing this, representing a single node within the tree. So we're calling this class tree node. And it has a constructor function. It simply takes a key and it sets self.key to key. It also has a couple of other properties, self.left and self.right, which are initially set to none. So each node, when it's created, exists independently of other nodes. And now let's create nodes representing each of these nodes. So we have node 0, we're calling tree node with the value 3. Then we have node 1 and node 2. So there you go. Now we've created the nodes and we can verify that it is of the type tree node. You can see here. And if we check the key of node 0, you can see that it has the value 3. And we can now connect the nodes by setting the dot left and dot right properties of the root node. So if you go to node 0 and set dot left to node 1, so now we've connected node 0 to node 1. And similarly, if we set node 0 dot right to node 2, now we've connected node 0 and node 2. And that's it, we're done. So now we have 3 nodes and then we've connected each of those nodes. And we may also just want to track which is the root node. So we can create a new variable called tree and simply point it to node 0. So tree points to the root node of the tree and then the root node is connected to its children and the children will be connected to their children and so on. So you can check here that if we check tree.key, we get 3. And if we check tree.left.key, so tree is the root node, it has a value 3. Tree.left is this node, so it should have the value 4. And tree.right.key should have the value 5. Okay, so pretty straightforward, and that's pretty much the answer to the question, implement a binary tree in Python. Now going forward, we will use the term tree to refer the root node, to refer to the root node, and the term node can be used to refer to any node in a tree, not necessarily just the root. Okay. So here's an exercise for you. Try to create this binary tree. So now you have a root node here and then you have a left child and right child. And then this left child has another left child but does not have a right child. Similarly, here you have another right child and then it has a left child which does not have a left child but has a right child. Okay. So there's a slightly more complicated tree structure and try to use these cells, these empty cells that are given here to replicate this tree structure. And then try to view the different levels of that tree manually. Okay. Now please do that because that's a great exercise in understanding how the structure works and how to connect the nodes. But it's a bit inconvenient to create a tree by manually connecting all the nodes. In fact, here you may have to make a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 connections, right? So what we can do is we can write a helper function which can convert a tuple. And the tuple will have this kind of a structure. So a tuple is kind of like a list, except that it is represented with these round brackets of parentheses. So a tuple will have this kind of a structure. It will have 3 elements. And then the middle element will represent the value or the key within the root node. The first element will itself also be either a tuple if the left child is an entire subtree. Or if it is a single number, then it will be just a number. And then the right element will represent the right subtree. Okay. So here's an example. Here is one tree tuple. Now, if you see this tree tuple, it has 3 elements. This is the first element. This is the second element. And then this is the third element. So this first element 2 represents the root node. And then this, so this second element 2 represents the root node. This first element or element at position 0 represents this subtree. So you can see here that in this subtree, if you look at just that subtree of that tree, 3 is the root in that subtree, and then 1 is the left child, and there is no right child. So that's what this represents. And then for this subtree where 5 is the root node, and then you have 2 other subtrees, that's represented here. So 5 is the root node, and then you have a subtree here and a subtree here. So this is a very easy way, this is a convenient way for us to represent a binary tree. And what we can do is we can define a function parse tuple, and this parse tuple function can take a tuple like this and then convert it into a tree-like structure of linked nodes using the tree node data structure, using the tree node class that we have defined above. So we call the parse tuple function with some data, for instance, this tuple. And the parse tuple first checks if data is of the type tuple and it has a length 3. If these two things hold true, then first we create a node. We create a node with data 1. So in this case, we create a node with 2 as the key. And then we set the left and the right subtrees of the node. And then we're doing something very interesting here. We're calling the parse tuple function once again. So we call parse tuple this time. So this is called recursion. When a function calls itself inside it, that's called recursion. So we call parse tuple with the first element, which itself is a tuple, right? So once again, that it calls another invocation to parse tuple. And for a moment, let's assume that that returns the proper subtree, the proper node. So we set that node, which got created, to node.left. And similarly, we create the right subtree using these values. And then we set that node to node.right. Okay. Now, you might wonder, in the function we're calling itself, so when will this stop? Can't it go on forever? And that's where you have to track the actual function calls. So when we call parse tuple with the entire tuple, first it calls parse tuple with this. And when you call parse tuple with this, then you can see that 3 is used to create a node, and then parse tuple is called with 1. So when parse tuple is called with 1, this condition no longer holds true. And we also check the next condition, which is if the data, if 1 is none and 1 is not none. So this condition does not hold true. So we fall into the else condition and we simply create a node, right? So we just create a node, and this time we are not calling parse tuple once again, right? So this is called a terminating condition of the recursive function. And similarly, once we get back the result from 1, then we call parse tuple with the value none. Once again, this condition is not entered and this condition matches. So we set node equal to none and then we return the node. Okay. So when we reach either a leaf node, which is either a single number, or we reach the value none, that is when we stop invoking the function recursively, and then the function returns, and that's how the entire tree gets converted. So this is a very powerful idea in programming, the idea of recursion, the idea of functions calling themselves. And it can seem unintuitive and confusing at first. So one thing you can do is you can add a print statement here inside this function to see how it works, to see how the different calls are going. So when you call parse tuple with the entire tuple, what are the internal calls that are made, and study how the result comes out. Maybe try it on pen and paper, but it's a very important technique for you to learn. You will be asked, or you will find applications of recursions in many places throughout your programming or data science career. So do learn it. So let's now call parse tuple with this tuple as an input. And let's see, okay. So that returned a tree, and then that tree is of the type tree node. That's great. And now let's examine the tree to verify that it was constructed as expected. So now we check tree2.key. So tree2.key should be pointing to the root node, which has the key 2. And then let's check the level 1. So that was level 0. Let's check level 1. So let's check tree2.left.key and tree2.right.key. You can see here we get the values 3 and 5. Let's check the next level. On this level, we have tree2.left.left, and then we have tree2.left.right, but there's no value there. So we can't really check for a key here. Then we have tree2.right.left and tree2.right.right. So you can see that tree2.left.left.key is 1, but tree2.left.right is none because there is no child here, no right child. Then we have left.key and right.key, and that gives you 3 and a 7. And similarly, you can now check level 3 as well. So here are all the levels of the tree. So it looks like the tree was constructed properly. And you can see the power of recursion at play here, that the recursive function can now construct trees of any levels. Now you can create tuples within tuples within tuples, and as long as they have the right structure, as long as you have this 3-element structure where the left element represents the left subtree, the right element represents the right subtree, and the middle element represents the current node, you can construct a tree of any size. So now here's an exercise for you. We've defined a function to convert a tuple into a tree. Define a function now to convert a tree back to a tuple. So if you have a binary tree, return a tuple representing the same tree. For instance, for the tree created above, tree2, calling tree to tuple should return this original tuple which is used to create the tree. And here's a hint on how to do this. Use recursion. So do fill this out and see if you can figure out how to do this. So now we have defined a class for a binary tree, and we also have a way for creating a binary tree from a tuple. So now let's create another helper function to display all the keys of the tree in a tree-like structure for easier visualization. So here we'll call this function display keys, and we'll not get into the code for this because it's a pretty straightforward, but there are a few conditions we need to handle. But here's what it will give us. When we call display keys on a tree, then we'll get this kind of a representation of a tree. And you can see that this is not exactly the same representation as this. You will have to take this representation and then mentally rotate it by 90 degrees in the clockwise direction to get a representation like this. But you can see roughly that the root node is 2, and then it has a left child 3 and it has a right child 5. Then 3 again, it has a left child 1 and there is no right child. Now 5 has a left child 3 and 3 has no left child and 3 has a right child 4 and so on. So the exact same structure has been replicated here for us to view visually. Now this is a very useful thing. We're spending all this time here talking about how to create trees and how to visualize trees, because the easier you make it for yourself to create trees, the more likely you are to test, the easier it is for you to test different scenarios out. So always spend a little bit of time coming up with good string representations for any data structure you create, something that helps you visualize them, and an easy way to create these data structures. Okay. So now we have a way to visualize the tree as well. That's great. Now here's an exercise for you. Try to create some more trees and visualize them using display keys. And you can use this tool excalidraw.com, and that's how these diagrams were created as a digital whiteboard. So you can create some trees. You can create trees like this, and then try to come up with tuples for those trees. Try to create those trees using the parse tuple function, and finally try to display them. Okay. So experiment with it and explore what are all the different tree structures that you can create. Now the next one of the frequently asked questions in interviews is to traverse a binary tree. Binary tree traversals are very common. So you may face one of these three questions: write a function to perform the in-order traversal of a binary tree, or write a function to perform the pre-order traversal of a binary tree, or write a function to perform the post-order traversal of a binary tree. Now, what do you mean by a traversal? A traversal refers to the process of visiting each node of a tree exactly once. Now, what do you mean by visiting? By visiting, it could mean any operation, but generally it refers to either printing the key or the value at the node, or adding the node's key to a list. And then there are three ways to traverse a binary tree and return a list of visited keys. So the first one is called in-order traversal. And the in-order traversal, now traversal is defined recursively because binary trees have this recursive structure. So you will see that almost all the functions that we write will have some sort of a recursive structure. So in-order traversal involves first traversing the left subtree recursively in order, then traversing the current node, and then traversing the right subtree recursively in order. So what does that mean? Well, we start out with this tree and we're traversing it in doing an in-order traversal. So we look at the root node and then we realize that it has a left child. So it has a left subtree. So we do not visit it yet, which means we do not print it or we do not add it to our list yet. Rather, we follow the path on the left side and then we come across 3. And then we realize that, okay, 3 also has a left child. So we don't visit it yet. So then we go down to 1. We go down to 1 and now it does not have a left child or a right child. So we can visit 1. Then we go to 3 and now we visited the left subtree of 3. So now we can visit 3. And then the next step is to visit the right subtree of 3. But of course, 3 does not have a right child. So there is no right subtree to visit. So we can move back up to 2. So now we've visited the left subtree of 2. So now we can visit 2. So we print 1, 3, 2. And now once we've visited 2, we can now visit the right subtree of 2. So to visit the right subtree, we go to 5. Once again, we realize that 5 has a left subtree. So we go to 3. Now 3 doesn't have a left subtree. So we can visit 3. Then we visit 4. Then now since we visited the left subtree of 5, we can now visit 5. And similarly, we then visit 6, 7 and 8. Okay, so that's the in-order traversal of the tree. And then there is another traversal called pre-order traversal, which is slightly different, where you traverse the current node first. So here we start out at 2 and we say that, okay, we're going to visit 2 first. So we visit 2 or print it or add it to a list. Then we traverse the left subtree and then we traverse the right subtree. So we visit 3 and 1 and then we come to the right side. We visit 5 and 3. So you can compare these two diagrams and see how in-order and pre-order traversal are different. Now these are very important for you to understand because they are great examples of different functions which have very similar implementations, but there are just 1 or 2 things you will need to change. And these are recursive as well. So do understand the subtle difference between them. And second, they are very commonly asked in interviews. You will most likely face some coding assignment or an interview where you will be asked to perform a traversal of a binary tree. And then finally, there's another traversal called the post-order traversal. And I'll let you guess how it works. You can also look it up. And here's an implementation of in-order traversal. Now it may seem a little complicated, but it's actually pretty straightforward. So let's look at it here. What we do is, given a node, we first traverse the node's left subtree. Then we create, so that should return a list of all the keys. And then we create a list with just the node's key. So we get the list of keys from the left subtree with the in-order traversal. Then we add to it the current node's key. And then we call traverse in order with the right subtree. And that recursively keeps adding these keys, each one. And the end condition, so the terminating condition for the recursion is when we hit none. So when we hit a node which does not exist. So that means we come there from a parent which does not have a left or right child. Then we return the empty array. Okay. So let's try it out with this tree. So this is the tree we have and we just saw its traversal. Now if we traverse the tree in order, we get the values 1, 3, 2, 3, 4, 5, 6, 7, 8. And we can verify here. We have 1, 3, 2, 3, 4, 5, 6, 7, 8. So that was the in order traversal of a tree. Now the exercise for you is to print the pre-order and post-order traversal of the binary tree. And you can test your implementations by making submissions to these problems on leetcode.com. Okay. So that was our discussion about traversals. Another thing that you may get asked commonly is writing functions to calculate the height or the depth of a binary tree and then writing a function to count the number of nodes in a binary tree. Once again, these can be expressed recursively as well. Now the height of a tree given a node is simply 1 plus maximum of the height of the right subtree or the left subtree. The height of the tree is defined as the longest path from a root node to a leaf. So you can see that the longest path from a root node to the leaf is of length 4. So 2, 5, 3 and 4. And the way to get the longest length of the longest path is by checking the max of the left height, right height, and then adding 1 to it. And of course, the terminating condition here also is if you hit a node that does not exist, you return 0. So that's how you get the height of a tree. And you can check that the height of a tree is 4. Then here's another function to count the number of nodes in a tree. Once again, really simple. All you do is this time, instead of checking the maximum, we simply get the size of the left subtree, get the size of the right subtree, add them and add 1 to it. So here you can see that there are 9 elements in this tree, 3, 6 and 9. So we get tree size of tree as 9. Now here are a few more questions relating to the path lengths in a binary tree. So you can just check. There's a concept of maximum depth and minimum depth, and then there's also the concept of a diameter. So you can try out both of these. Now, as a final step, what we can do is we can compile all the functions we've written, all the methods as methods within the tree node class itself. And this technique is called encapsulation, where we are encapsulating the data as well as the functionality related with the data or the data structure within the same class. And this is really good programming practice. So as you write more code, try to think about how you can create these classes with not just the information inside them, but also with the relevant methods inside them. Okay, so we've now added the methods height, size, traverse in order, display keys, toTuple, and we've also added these methods str and repr. And remember quiz 1, you can go on LinkedIn and post an answer to what these functions do. And finally parse tuple as well. So all of these functions are now added within the class, and you can try it out here. So for instance, here we have a tree tuple, and we can call tree node.parseTuple to convert this tree tuple into a tree. So you can see that now we are also representing the binary tree itself using this tuple-like representation, but we can also display it in this hierarchical structure using display keys. Then we can check the height using tree.height. We can check the size using tree.size, and we can traverse the tree in order using traverse in order, and we can convert the tree to a tuple using tree.toTuple. So do create some more trees and try out the operations that we've just defined, and you can also try adding more operations to the tree node class. And before continuing, we can just save our work. So I'm just going to import Jovian and run jovian.commit.